Good morning, sir.
Good morning.
Yes, sir. We're in the lab today also, sir. Sir, we can start by 10, na?
No problem.
Yeah, okay, sir.
My voice is audible, right?
Yes, sir, it's audible.
Okay, thank you.
Yes, sir. Sir, can I start?
Yeah, no problems.
Yeah,
Can start.
yes, sir. Yes, sir. Yeah, so very good morning, dear participants. Now we are entering into the first session of the third day of STTP. And now we have the expert from NIT Surathkal, Dr. B. Venkatesha Perumal sir with us, who is handling this session on control of grid-connected PV inverters. Hearty welcome, sir. It's my privilege and honor to introduce Venkatesha Perumal sir, Professor, Department of Electrical and Electronics Engineering, NIT Surathkal, to the participants of this one-day STTP. Sorry, 1 week STTP. Dr. Perumal sir received his PhD degree from IIT Delhi in 2007, and he has 11 years of experience, which include both teaching and industrial experience. Like before joining NIT Surathkal, he served as a faculty in VIT Vellore from 2001 to 2003, and later he served as a manager R&D BPL Healthcare Bangalore, senior design engineer GE Bangalore, senior design engineer APC Bangalore, and he worked as a senior design engineer and technical lead in power electronics section in Sun Edition India till 2015. And he also served as a head of the department and in different administrative capabilities, including the Senate member, professor in charge of NITK, STEP Center, etc. So he has more than 22 publications, journals in his account, which includes publications in IEEE transactions on industrial electronics, energy conversion, circuits and systems, industry applications, etc. He bagged several awards, which includes Bharatidasan Award, like for the first position, which he secured in his ME in Power Electronics and Drives, received Innovative Student Project Award in 2008. That is a doctoral level award received from Indian National Academy of Engineers. Then Landsteiner Award for solving HFA control board issue in GE, Teamwork Award from Advanced Solutions Sun Edition in 2014. He has completed 6 sponsored projects under DST, NITK Institute sponsorship, Infineon Technology, Raptor Design Technology, etc. And he has 4 ongoing projects now under the Department of Heavy Industries, Raptor Design Technology, and funding from Alumni, NITK, etc. Under his eminent guidance, 2 students completed PhD and 3 scholars are pursuing PhD now. Furthermore, he has 2 granted patents in his account and 5 applied patents. He is a renowned academician and researcher who has provided many significant contributions in the area of solar PV systems, wind energy conversion systems, and in PMSM drives. Warm welcome, sir, again. Now I request Dr. Professor Perumal sir to start the session.
Thank you. Thanks for the introduction. I'll share my presentation. I'll share my thing.
Yes, sir.
Are you people are able to see my screen?
Yes, sir. We can see.
Okay, so good morning to all. Today I'm going to present the topic is control of grid connected PV system. Basically, I wanted to give the introduction about that PV first, and then I'll take you to the step by step where why we need a control in a grid connected system and what kind of a control is required for this particular one. Basically, what kind of a control is required for the grid connected system. So I'll take you in a sequential manner so that it will help you to understand and design the system. I have given the my presentation outline. I will talk about some introduction about that PV systems, and then I'll be giving talk about that PV cells. Okay, types of PV cells and what is its equivalent circuit, how we are going to analyze all those things we are going to see in the subsequent slides, and VI characteristics and how the power variation with respect to the PV cells when it is operating with the different conditions, and effect of partial shading, why MPPT is required, and effective design of MPPT and on-grid system. So whole objective of this particular presentation, not only concentrating that okay only the control is very important, so but I wanted to emphasize that why the control is required, what for we are doing, all those things I wanted to set the platform before going to the control. So if you take it that solar system, basically solar system, we can take it in a energy extraction. One is a direct method of extracting the energy and utilizing it in a direct form. The another one is indirect form, which is basically converting that solar energy into electrical and use it for a different application. So in case of direct application, the water heater. So you know what kind of a water heater. So basically the mechanical people will be involving much on this, because how the collector is designed as a solar irradiance to be collected and transferred directly to the water or any media, and it will go to the heat transfer mechanism. It happens. So as an electrical engineer, we are not much bothered about that, the direct conversion, but here in the indirect conversion, the solar energy, how we are converting this and utilizing it. So it goes into the two form. One is off-grid and another one is on-grid. In off-grid, what exactly the application is? If the power available is there, I can store it in a battery, or I can, whenever the power availability, dumping into the battery. Battery will regulate for my load requirement. Another interesting application in off-grid is one of the things is the solar water pumping, because the induction motor has that natural behavior, V by F ratio control. If I do that, the power variation will happen. So I can control directly. So that is where the solar water pump were emerged. Coming to this on-grid. So in on-grid connection, we have to export the power, which is a DC generated. The power here, the DC current source. What we have as a PV is a DC current source. We need to get it. So how we are doing that, that is where it is very critical thing, how the power electronics converters comes into the picture, and what kind of approach we need to do to extract it more. Those things are comes into the picture. So basically in grid connected, when we say grid connected, immediately any source, any type of source, you wanted to connect it with the grid. I'm talking about the source. Any source, if you are talking about the thing is, if you wanted to say that the grid is need to be connected, means here you, so basically we have to use the one source to another source synchronizing mechanism. So first thing is comes into the picture, synchronizing things. When we do the alternative, two alternative synchronization, we used to look after that the phase sequence and the magnitude and frequency matches closes, and then we connect. So in case of here the on-grid system, when you use the PV grid inverter, the same thing is to be taken care over here first. Otherwise, you can't export it power to the grid. Okay, so the same good old technology which is for synchronizing, the same concept need to be applied here for the on-grid system. In subsequent slides, we will see in more how it is connected and what way it is, how all the implementation point of view. The topic which I wanted to say here is, previously I said overview, what is the application and other things. But when the power generation happens in the PV cells, okay, so PV cells, again, if you look at it, it has that the three types of PV cells: monochrome, polycrystalline, and thin film technology. So monochrome, you can see here the grains are oriented. You will not see any zigzag in the cell orientation, but you can see here there is a cell orientation is not present over here, and you can see that the orientation of the cells are not proper, grains are not proper. Here, this thin film technology is altogether, it is a different technology compared to this monochrome and polycrystalline. The monochrome technology, you can see that by looking at the panel, how we can identify whether it is a monochrome or a polycrystalline or thin film. Thin film will be a dark one, you can easily identify. At the same time, for polycrystalline and monocrystalline, if you see that the clearness on the cell aspect, and these two lines are, we can call it this one as a bus bars in the cell. Okay, so positive bus and negative bus, what we connected, that's what it is. It is all over the panel. If you see the panel, its number of cells are connected through these lines only, it is connected. Now, if you look at it, how the silicon is extracted. So if you see that silicon extraction, and it is a tedious process, the energy requirement for this particular one is much higher. And the raw silicon is molten form and purified and taken it in the form of cylinder and cold it, and perfectly it will be cut as in the wafers. So the wafers will be cut when it is in the cylindrical form. Just a second, the thing is, I'm not able to explain it with the marker. I'm changing my slides into a PPT mode so that it will be easy for me to draw and show what exactly I'm trying to explain over here. So basically, if you look at it, the monochrome cells here, it is, you can see here the edges were cornered over here. While extracting the material, silicon material, it is in the tubular form. The energy requirement for this particular one is very high. People normally talk about that the solar is a pollution free. When I reiterate that term, solar is not a pollution free. Solar power generation is pollution free, because the solar cell manufacturing produces a lot of pollution. You can go and check it in YouTube, how the cell is extracted, the silicon cell is extracted. If it is in the tubular form, the energy consumption for this one is more. So what they have used it, if I cut it exactly the square, and already this material is processed over here, so the material wastage is going to be more. So if I draw here, the wastage on the material will be more if I cut it in the form of square. Instead of that, I'm trying to use that more area by using the octagon shape. So the wastage is going to be minimal, and at the same time energy efficiency is going to be improved on this monochromes. So the monochrome efficiency is higher, polycrystalline efficiencies are low, and thin film again efficiency is very high. Thin film technology altogether, the technology wise it is different, and it gives that the efficiency much higher value, it's around 20%. But in case of monochrome, we get around 15 to 20%, and then polycrystalline, the efficiency is around 13 to 16%. Okay, just I wanted to say that the PV cells are made in this form, and number of cells are going to be connected in series. Now we have seen one cell which is connect. We have cut and we got this. So this can give only my 0.6 volt or 0.7 volt. Okay, 0.6 or 0.7 volt. Now one cell can produce that 0.7 volt. If I take it, I can't generate it. It's a current source. Basically, it is a current source. Depends upon the irradiance, I'm going to get the output, current variation. So you can see that I have put here, it's a PV representation. This is one cell. Even if we put panel, we put the same thing. So panel is going to be much more number of cells. Okay. Just coming to that, one cell we know the corresponding equivalent circuit. If I look at it here, NP is nothing but a number of parallel cells. So here I have not used any parallel cell. You can put it 1. That means this photon current, light current, which is coming out here, it goes into the Kirchhoff's current law. If you apply, we will get that ID and IS, it goes down, and finally we are getting I. So what we are interested in the cell, if you look at it, this is the current, which is the current. This is the current is meaning for me in this voltage and this current, it makes that my power. So the power output from the solar cell indicated over here. So to calculate this current, the current generated current minus of these two current. So this current basically the diode current. Okay, number of series cells are which is connected here. This current is basically the current flow through the shunt resistor. And this is my light current. I'm getting the equivalent circuit based on that output current I will be getting. Now, if you see that each and every parameter, if you go and look at it, the basic diode current equation, from there it is emerged. So if you look at it, the light current, what it is basically is the photon current. So the short circuit current, temperature dependent, and this one is the irradiance. Now, most of the people think that the solar generation is very good for our country because our country temperature is very high. No, actually, for the PV cells, if you look at it, the PV generation will work very well if the irradiance are high and the temperature is low. Okay, temperature is low. If the temperature is more, the power generation is going to come down. Okay, and the irradiance is high, the power generation is high. At the same time, temperature and irradiance both are contradictory. So irradiance, light should be there, but it should not create any temperature effect. So you can see that exactly what are all the components it's related into the current. Now, diode current, if you wanted to calculate, again it is going into details of the physics involved over here, all the component of current, how we are calculating the photon current. So when we look at it, any design, first I said about that solar cells, I wanted to make it now solar cell into a panel. Here I have taken the data sheet, the LG400N2W-D5. What exactly the data sheet parameter? We need to look at the data sheet parameter. We will get the input because this is my input side. Whatever I spoke to you before, it is only the fundamentals, what it is related with the solar cell. Now, looking at the data sheet of the panel, because as an application engineer, I will look at the data sheet of the panel, what it is, what I am going to use. So you see that monocrystalline N-type and LG is the main. Configuration they have given here is a 72 cells. 72 cells. What is that meaning? Here, 72 cells are connected over here. Okay, so basically, each one of them or one cell, if I take it, I am connecting 72 cells in series. Like this, I am connecting 72 cells, it goes from 1 to 72. This makes, again, you can see that cross 6 it is given. What is that cross 6? It is 12 cells once it is divided as a one bypassing diode over here. So 1 to 12, I have a 12th diode. If I cell, if I have, this contributes one diode. So I have a 6 diodes which is anti-parallelly connected in the panel. You can see the back side of the panel. If you open up the junction box, you can get that how many diodes were connected and what form. You can correlate with the data sheet. So this gives me and now 72 cells, how that configuration is done. 72 cells are connected in series only. Now this is another panel size and glass or all other things. This IP65 is nothing but the standard which says that it environmentally, if I put it outside, nothing will happen to the system. Another one is connector connector is nothing but MC4 connector. This is the standard connector which will be used for the PV system. Now, looking at that, this is overall parameter what it is there. Now, coming to that electrical parameter, if you look at it, the maximum power at 400 watts it can deliver. The MPP voltage is 40.6 and MPP current is 9.68 ampere, say 9.86 ampere, and open circuit voltage and short circuit current. Maximum efficiency on this particular module is 19.3. So you have to look at it. This is a monocrystalline, but we are getting the efficiency is 19.3. Power tolerance is also given. And this is standard test condition. What is that standard test condition? If the irradiance is available 1000 watts per meter square and cell temperature is 25 degrees. It's not ambient temperature. He's talking about the cell temperature. Okay. So the temperature is 25 degrees you will get. If I look at it in the normal condition of Indian condition, this 25 degree is not going to happen. We will be around 35 degree normal degree centigrade. And 1000 irradiance is also, we will not be able to get it all the time. Okay, so whatever the irradiance are coming, it varies with respect to the sun position, because our panels are fixed. Even though if you track also, you will not get the maximum of 1000 irradiance from the sun. So whatever the climatic conditions, it affects. So 400 watt panel if you put, you will not get the 400 watt. How the much variation and other things. So before going to those things, other parameters which are there in the panel, you can see that these are all the standards it has to meet. Okay, it has to meet. And if you look at it, this UL conditions, the one more parameter will also come into the picture, which is string voltage. If I have a one panel which is having a 72 cells and its voltage is 40 volt, I cannot connect 100 number of panels in series to get the voltage. Okay, so 100 panels if I connect it, my voltage is, this is 100 panel. If I am taking 72 cell 100 panel, 100 into 40 volt it will come. So this is going to be 4000 volt. This is not permitted in this case. The string voltage normally it will be restricted to 1000 volt. Okay, and presently people are thinking to go for 1500 volt. Okay, but still the present days whatever the in the field is, only 1000 volt is the DC bus max. So that is indicated by this UL. Okay, so UL rating will take care on this particular aspects. That's why I wanted to put over here that UL rating. Now at a nominal normal module test temperature, you see that irradiance is 800 watts per meter square. Ambient temperature is 20 degrees centigrade. Wind flow and other conditions. This is the variation. Percentage of degree is increasing. The temperature is increasing. The power will be reduced by that 0.36 percentage. Similarly, the voltage will come down, but the current is increasing. The meaning is here, the curve, if I draw for PV curve or VI curve for the solar system, if I draw, the temperature is increasing. Under that condition, short circuit current will increase, but the power will decrease, and the open circuit voltage will also come down. So that is what indicated by this negative sign. So most of the panels, whatever we have, it's a negative temperature coefficient. If the temperature is increasing, the power is going to come down. So while designing that, we have to be very careful where we are going to install the plant or where we are going to install the system. That is also important from this particular one. So you see that at nominal condition, so whatever that Okay, module operating temperature, the above mentioned condition, we are getting only 300 watt. Okay, so if I do that, the wattage is going down, and all other parameters, if you can see that the variation how it is happening in the power. So the first point which I wanted to set here is when the temperature is increasing, the power is coming down, and the thing is, it is, if the irradiance is very high, the power will be very high. Even though if we take it 400 watt panel, we will not be able to get the 400 watt out of the panel. Looking at that IV curve, so what kind of system it will come here, you can see that for 200 watt, what is the condition? 4 watts per meter square. Sorry, 200 watts per meter square and 1000 watts per meter. So 1000 watts per meter square. How the curve is varying. So it has given for the different conditions. What we can take it into the consideration for the design purpose. Just coming to the photovoltaic panels. So here, whatever we have showed, this is one of the plant which is having the inverter at this point. Number of panels over here. So many number of panels which are connected. It is a central inverter. It is not a string inverter or it is not a micro inverter. It's basically a central inverter, 1 megawatt system. Here you can see that number of panels were connected. Finally, it is coming to the inverter location, and then the power generation is happening. So this particular case, I wanted to show that what is the normal VI curve. So if you look at it, normal VI curve, this is going to be the curve, and PV curve is this one. You can see that this is my operating point, the maximum point in the curve. So if you do the product of V maximum and I maximum, we are going to get the P maximum over here. Now, coming to that, how the variation happens. In the sun rises, it goes to the peak and it comes back. You can see that the open circuit voltage, this is a kind of array voltage. It is not an individual panel voltage. Here, whatever I showed in this particular case, it is an array voltage. So solar array voltage is also varies because the irradiance is very low. Now you can see that MPPT is also varying. MPPT point is also varying. With respect to the sun position, we have to change that operating point to extract the maximum power. This is one thing, variation with respect to that warm day, temperature variations. Okay, temperature variation, how it is going to affect my current profile and power profile. If the warmness is more, then the things are getting megawatt generation. We have to see how the power with respect to the different irradiance with the warmness, basically the temperature variation, how it is going to. If you correlate the previous slide to this slide, the power generation at the same irradiance, when the warmness is high, the power generation has gone down. So you have to correlate the previous slide and this slide, how the temperature is affecting my generation. So this is basically what I was talking about as the panels which are connected in series. Directly I can extract it the power. But one more condition when it comes, you see that the condition where I'm talking about is a partial shading. Partial shading means what exactly? The term I wanted to define first. I have a panel which is connected as an array. All of them are connected in series. All of them are connected in series. So under this condition, the current flow through this particular point, here it is I, this is also going to be I. If the panels are connected in series, I have the current flow through this one is constant. Here you think of all are getting 1000 irradiance. Then there is no problem if this is a V1, this is also V1, this is also V1, this is also V1. We will get the power at that the current is high and the voltage here it is going to be around 4V1. But here you think of this particular one is getting shaded. If I completely shade this particular module, the meaning is completely shutting down this module, meaning is I don't generate any power over here. That means the voltage at this point is 3V1, but the current is still high. So the current is bypassed over here. We can use it the bypass diode. Think of if I have 1000 panels, will it be able to use the 1000 diodes? So it is very, very difficult. The design aspect we need to take care. Another one is I was talking about that data sheet. If you see that data sheet, bypass diode, that is basically individually here. If I have a 72 cells, 6 bypass diodes were there, 12 cells were connected in series. In case of one cell is getting defective, under that condition, internally this bypass diode will come into the picture and your power generation variations are going to be reflected in your system. Okay, so the series current is affecting, then your power generation is also going to affect, because other panel is able to create the current is high, but this panel is, if current is less, under the series connection I can't get it this particular amount of current, my power variations are going to happen. So that is what I wanted to say here. In case of we have connected some 8 panel just to show the partial shading effect. Under normal condition 900 watts per meter squared, I have this particular one. Actually this is this condition is somewhere mismatched. This is not the one. So where the patent 3, here you can see that first one panel getting that higher irradiance, afterwards the voltage is going down. The meaning is here, if I have a first panel characteristics, this is my second panel characteristics, third panel characteristics. In case the second panel is getting shaded here, so your output is going to be restricted like this. If the third panel is even though if the irradiance is here, you will not get the like this. The profile, if I look at it, if the second case is varied, it will be like this. So the variation in the shading is also important. Now, one thing is, if I look at it, this particular point, this is the voltage at which I'm getting the maximum power. Previously, we have put that 2 lines which will be giving my variation in power within this band. But now, if I look at it, the power is happening here, 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 different locations. It is not restricted with the one location. So the thing is, we need to address these kind of things. Why we need a MPPT? So for this particular aspect is to be addressed by varying the band. By varying this band, we can get the varying this band over this range we can get. But look at the aspects, how you will be doing this variations. Another aspect, most of our researchers put the paper, my MPPT algorithm tracks all the global peak. But still, what I wanted to know is, my voltage is very low. Think of boost converter, normal boost converter. If I have boost converter, I can get the boost ratio is maximum 2. I cannot go beyond this. Practically, we will not be able to go beyond the 2. But here, you see, this is the voltage, initially operating voltage. My load requirement is going to be a 60 volt. think of it is a 60 volt initially operating here. My maximum power is here. Under that condition, it is going to be 16 volt. You wanted to 16 volt to be increased to 16 volt to boost to 60 volt. If you do that, what will be the component effect and what is the cost of the circuit is going to be? The inductor design will be overrated for addressing the other end problem. So while designing, we have to be very, very careful up to what point I'm going to track. The tracking is one point is very, very important to make sure that maximum power is extracted. Why maximum power is extracted is important. In case of PV, the efficiency is very, very low. Efficiency is low. To address that, I need to extract it more power given point of time. At the same time, the cost involved in this. So how much time this kind of a shading pattern is going to happen? Okay, if it is going to happen very rarely, no need to address this thing. You can restrict your band only in this region. That itself it holds good for the product point of view. Okay, in the research also we can say that optimum maximum point region has been covered from this point to this point. No need to cover up that entire point. If the MPPT is happening at 5 volt and my load requirement is 60 volt, you wanted to address this will involve a lot of cost. So first thing is, I said that the MPPT condition, we need to track the effective point, utilize that maximum circuit bandwidth, because what I'm trying to say here is how much band we can go and use it. Return on investment is also important for this particular case. So one of the algorithm which I wanted to say that just for understanding purpose, this we have done it and we have implemented and we have seen the results also. Okay, that's where I thought I'll present it this, so it gives that more impact on what is the global MPP. So basically, normal circuit, if I look at it, my circuit point of view, here you can see that this is my PV curve and IV curve. Operating point is here. The perturb and observe. Slightly, I'll give that perturbation and see that whether it is operating here or not. I'll be checking. But if the case here, you can look at it. This is the equivalent circuit of the entire system. One more condition, you can see that normally the P maximum point, maximum power point tracking, it happens with the 0.9 times of VOC. Similarly, 0.9 times of short circuit current, this maximum current. It's a thumb rule kind of a thing. Most of the cases, if you look at it, the data sheet, you will come to know that exactly these points are matching. So this is normal curve when it is operated. But the one of the condition where we have wanted to show that this is my basically this is my maximum MPPT point, but if you operate it here, this is my MPPT point. Normal perturb and observe method, if you do that, it will change here, it will go here, yeah, power is reducing, it goes back. It will come this side and goes back. So perturb and observe, perturbation and observe the results, and it goes and it will push back here. But what we wanted to do that, this is for the global MPPT point of view, to show the effectiveness. So don't get take it away that this 25 volt, if you are operating here, it is a 70 volt and this is 25 volt, boosting of this one is working or not. To show the performance of the proposed algorithm will work here even. That's why we have showed this particular area. How the system is working, you can see from the flow chart. So when initially whatever the operating condition, so initial condition here we talked about this A. Okay, so from the initial current and voltage, everything we have checked it. I reference is set here because this is a current control. I reference is set with the present current. If you see that the current will be divided by 0.9 and the reference current is equal to whatever it is, whether it is equal to I or not, we check. And the measuring power, we check that power is greater than maximum power, the stored power, because here we calculated this power, and checking with that, is it greater than the calculated power or maximum power, no or yes. Again, updating the values, it goes, keep on, it goes to the loop. The meaning is it travels from the point A to D, A to D, and once this is attained, it will come out and it goes back to the other side and track the efficiency. Again, it goes this side. You can see this L. Again, new operating point will be shifted to the D. So this algorithm we have implemented and we tested it. This works very well for the global MPPT point. But I don't suggest this one for the wider voltage range. To show the performance, we have done it this kind of a control. And the same thing we have simulated with the buck boost converter. You can see that what is the conditions, and to show that the effectiveness, all the parameters also here we have specified, and the condition at which what it is happening. You can see that the profile over here, PV voltage and current power profile, how it is, and under partial shading condition, because it is all or 900 watts per meter square, and in between, if it is changes, this gives the partial shading, and the other one is, and again increasing in a different way, how the tracking point is achieved. So basically, we have done the simulation, and that simulation shows that you can see that tracking time. So tracking time is also very important in any algorithm. So the tracking time, whatever we have proposed, one for reaching the maximum, is very less compared to that whatever the methods are in the literature. So basically, this is for the tracking, the same algorithm we implemented, and we got this kind of a result. So the same thing here, we have developed that hardware setup over here. You can see this. This is my boost converter setup, and DSpace is used over here to generate the control algorithm. And we have done this particular one to check the performance. Okay, so this is the proposed one, and this is the other method which is available in the literature. So I hope you understand why we need to track the MPPT. So now I'm going into the real topic. So I made it the PV cells, how it will be, and what kind of a system, how it is works, and input side, when I put the connector, how it will be working, why the MPPT is needed. That's all I have talked about. I'm going to talk about solar grid connected inverter from this slide onwards. So if you look at it, the structure, what is the basic structure of a solar PV inverter? If you look at it, it goes with the panel, photovoltaic panel, and it has the power conversion unit. Basically, the power conversion units are boost converter and three-phase voltage source inverter. Whatever it is, voltage source inverter with the current control mode or voltage control mode, whatever it is, it's a three-phase inverter over here. Another front end side, that front end side meaning is PV followed by the PV connect panels, followed by the boost converter, followed by the voltage source inverter, and it is connected with the low pass filter, basically LC filter here we talk about, and connected to the grid. So this is the structure which is gives my power line diagram from this point to this point. So what I need to do, I have to do the MPPT by sensing the voltage and current on the PV side. I'm triggering my boost converter. Okay. Another, how I'm going to control the three-phase inverter. I need to control the three-phase inverter. Power, whatever it is coming out of the boost converter, need to be pushed into the grid. So I need to monitor the grid. So this grid monitoring is done over here, and the power information comes from here. This is given to the control, with the control given to the inverter. So basically, the inverter control has the input is from that for front DC converter, to the inverter. So this is the basic solar inverter structure. People will be using, actually, if you talk about that solar grid connected inverter, broadly it is classified in central inverter, string inverter, micro inverter, nano inverters. Okay, presently the product is available up to micro inverter. Nano inverters are still it is in the research mode. The central inverter power, to see that there is no boost converter. Directly the DC photovoltaic liner, directly it goes to the three-phase inverter, and it is controlled mechanism. Whether really we are talking about the MPPT in case of center, if you look at it, no, because it is operates with one of voltage, which I showed in the when the irradiance varies, the power variation, how it is happening with the band of voltage. So that will be taken care only with the band of voltage. The partial shading cases for the string inverters are not taken into the central inverters are not taken into the consideration because it is going to be in 1 megawatt. Another point which I wanted to specify, in case of solar, we have a maximum of 1 megawatt system. Okay, 1 megawatt system. Also, the power generation from the inverter is going to be 380 volt line to line. 380 volt line to line. It is not in terms of or anything. It is 380 volt. So always it is pushed through the step-up transformer, where from the 380 volt to the grid side 6.6 kVA or 11 kVA line through the transformer. So central inverters are always having the transformer connected between the inverter and the grid side. Always transformer, if it is connected, the system reliability is very, very high. Okay, so system reliability is very, very high in case of central inverter. Another inverter is called string inverter. What is that string inverter? String inverter, it is up to 20 kilowatt. We can say that up to now people are making up to 70 kilowatt also. It is a string inverter. Basically, arrays are combined. So many arrays are combined. There they have a boost stage. They will be having a boost stage and then followed by the three-phase stage. So boost stage, what exactly it does is, so many array combinations, they use it for the boost converter configuration. So if you see, this is my one array point, and this is array number 1, and array number 2 will be combined, because array number 2 will be combined in the combiner box, and then it goes to the combiner box. Basically, it goes to the MPPT box, and then it goes to the DC to DC converter. Okay, DC to DC converter. It goes into the next stage is the DC to AC. So basically, here the number of arrays are combined used for the DC to DC converter, but in central inverter there is no DC to DC converter. In case of micro inverter, basically it is a panel level inverter. Directly the panel output is given to the DC to DC converter. The output of the DC to DC converter again given into the inverter. So micro inverters normally they work with a single phase. It is not a three-phase system. Okay, because the power level is below 5 kilowatt, the inverters can be worked with the single phase system. Above 5 kilowatt, the system is going to be a three-phase system. So in case of micro inverters, the wattage is going to be panel watts. Right now, whatever it is available, 450 watts panel. If it is a 450 watts single phase system itself, it is enough. So DC to DC converter followed by the DC to AC. So I'm more concentrate on the string inverter because that we have developed some of the inverters. Just I can show that some of the pictures and the tested condition. That's why I'm going to show only the string inverter. Micro inverter, again, if you look at it, the panel voltage is 40 volt and your grid voltage is 230 is a RMS voltage. To meet this voltage, again, that the inverter DC bus voltage need to be very higher. So boosting has to be done very higher way. So that normally they use as the high frequency transformers over there in the system. Now, if I talk about that inverter, first I need to know what kind of a standard it has to follow. So IEEE 1547 for the distributed generic energy sources where we wanted to connect. Another IEEE standard which is for the 51519 harmonics and voltage and current for the requirement. Another IEC requirement is for grid system less than 10 kilowatt to the low voltage grids. To the low voltage grids, we need to meet all these specifications. So basically, these specific certification requirements, basically compliances on this particular one, compliances to meet this IEEE standards, then only you can push the power to the grid. So pushing the power to the grid is by meeting all these requirements. What are all the requirements here? It is mentioned over here. If you look at it, it is basically the anti-islanding, low voltage right through. Mainly for the solar system, they will talk about the low voltage right through. In case of wind generation, they will talk about the high voltage right through. So here mainly we will be concentrating on the anti-islanding, low voltage right through, and some of the system requirements, harmonic levels, and reactive power support. Okay, so those things and all it falls under the category. Now, I talked about the overall block diagram, but as academicians, I should know how the system is working, and I should know that what is the model particularly for this particular system, proposed system. So if you look at it, this is my PV system. I have a solar is an input, and I'm getting the DC current. It goes to the inverter module, basically here, inverter, converter, whatever it is there. And this here I have a DC sensed voltage that goes to this side and completing my loop. Whether this inverter need to support the reactive power or voltage regulation, based on that the input will come. The output D axis and Q axis component will come. That will give the current or reference things to the grid. So basically I'm sensing the voltage here and pushing the current here. We can see that once again. Yeah. This particular implementation, I'll come back to this slide. Here you can see this is the model where I have a current is my DC current is coming from the PV panel. If I know what is my current, reference current, I'm comparing, integrate the current, you will get the voltage. So integration of the current 1 by C into integration of I is nothing but my voltage, right? Capacitor voltage. This is basically a DC capacitor, DC bus capacitor representation. It comes out as a DC voltage. Once I know the DC voltage, I can give it to the panel, whatever the panel representation. Now, getting the inverter current, how I'm going to get that real current? This is basically a real power current. So here I need to maintain the DC bus voltage. So DC bus voltage is taken as a reference, measuring with the DC bus voltage, measured component. And these two components are DC bus components are regulated, actually PI controller. I'm getting the current over here. Another component which I talked about, the reactive power and voltage regulation. In case of reactive power, you can see it's a voltage control, voltage bus reference voltage and sensed voltage From there, I can generate the angle, or otherwise I can generate directly the angle control. This gives my Y component, basically direct axis component and quadrature axis component of the current. Here, another component, you see that this is the PLL. Basically, this PLL, what it does is get the reference voltage waveform, sinusoidal component from the grid. So this is the voltage sensed from the grid. From there, we are getting the sinusoidal voltage. In case any angle control you wanted to correct, you can do it. Finally, you will get the D-axis component and Q-axis component. Here, the components are DC. Here, it is alternating. Okay. So this alternating voltage, and here I have a frame voltage, whatever this VD and VQ, I'm using the same thing as from here. With that, I can calculate the power. Power is nothing but VD ID plus VQ IQ. If I do that, I'm getting the power. Power is nothing but here is the system efficiency, lossless system, power divided by voltage, I'm going to get the current. So to analyze your entire system model, we can do it in this way based on the block diagram which I showed here. Now, what is that exactly we wanted? I want to show some of the pictures here. This is the 11 megawatt. It's a fixed tilt. Fixed tilt you can see here. Here, these kind of arrangements, the panel is rotates 180 degrees. So you can get that even the circular motion, so that the panel arrangement maximum power extraction. So that's why I have shown this particular one. So basically the cells forms the PV module forms the array again the array combined, you can get the more number of panels. This is for the PV system point. What exactly is there in the inverter? Present day inverters having only, this is the structure, it is a 2-level inverter. Now people are using only 3-level inverter for the swing inverter manufacture. But in case of megawatt system, still people uses that 2-level inverter. That's why I wanted to show very clearly and emphasize that this is basically a 2-level inverter. And if I have a 2-level inverter, my constraint here, what is the voltage requirement? As I said earlier, if you remember, it is a 380 volt is the AC volt. If it is a 380 volt is a line-to-line voltage, then what is my DC bus voltage should be? I need to calculate this DC bus voltage. And we have showed the 2 capacitor. Why we showed the 2 capacitor over here is because normally capacitors available voltage rating is 440 volt. So you can't use it that 440 volt capacitor for the entire bus. So we have connected them in series. When you connect these 2 capacitor in series, you will face the problem of voltage sharing in practical condition. So what we do is higher wattage, 10 watt resistor around 10 kilo ohm or 50 kilo ohm resistors will be connected in parallel with the capacitor, so that the power loss will be minimum because I'm using the higher value of resistor. At the same time, the potential will be equally divided in this case. So in case of inverter, we have to take care on this particular aspect. So before going in depth with the control, what is the utility concerns for the PV panels? So that is the first thing is the area control, where that the ramp rate at which rising and slowing down need to be very, very carefully we have to do it. The transient voltages stability, we need to look at it, because if abruptly changing the power, it should not impact any of the system which is connected near to the plant. Okay. Exactly, I was talking about that power quality and high voltage right through, low voltage right through, and islanding. So if you look at it, these aspects need to be covered. So one is a system ACE and normal contingency and power quality, high voltage right through, low voltage right through, and islanding, fault currents. So these are all the concerns from the utility point of view. before putting the PV plant into the system. So just coming to that, some of the slides information I have taken it from the SMA is a manufacturer of inverters. It's a German-based company. So they are the pioneer in this field more than four decades. Okay, so there I have taken some of the slides. You see that this is my inverter structure. Normally the panel which is coming here, I can connect it. From the utility operator, he can give the information to the controller setting that P and Q. Till today in India, none of the inverters are supporting the Q requirement. Basically, all the power generation, whatever it happens, the fixed P, and there may be a Q, but the Q value will be very, very low. It is set according to the site condition. It's not extensively used according to the condition, the variation in the Q. So with the step-up transformer, it goes to the grid. This is normal system when it is used. So also you see that the power management is to be done. One side we talk about that MPPT is important, but other side the utility people will say that okay, at this point of condition I don't want to be the more power to be injected by the solar. So that will be done by the that here it will be done by the utility people, either 100% or 60%, 30% and 0%. This kind of options are available in abroad. It is not happens in India. Okay, so they don't set it any conditions at present. So other requirement from the utility concern point of view, if you look at it, the voltage basically reactive power support. The reactive power is unity. That line is unity line. Either it can go to the leading or lagging. How we can support it? By changing the angle, which I said that. But why they restricted with in most of the grid PV inverter, people will be saying that if it is a 1 megawatt, I can use it the 1 megawatt during the night time. It is not possible because the capacitor DC bus voltage, DC bus capacitor value is not going to support the reactive power completely. So people normally think that when it's a grid tie inverter, if it is a 1 megawatt inverter, it will support that 1 megawatt during the night time. That is not possible because the capacitor requirement is completely going to change, the DC bus capacitor. So at present, what the most of the people gives that reactive power variation from 0 to 0.95. Okay, 0 to 0.95 power factor leading and lagging. What exactly it is indicates here, you can see that again that curve, the capacity 0.9 and it goes to that 1, and what is the band? So you can see that the voltage variation, if the nominal voltage is there plus or minus 5%, you can see that here it's a 5%, this side it's a 5%, here it is only 2.5. So 102.5 or 97.5, the capacitor voltage, the capacity VAR will be pushed to make the voltage stability in the system. Voltage stability can be achieved by injecting the reactive power. How much we can do? That is only this much. The percentage of Q, if I talk about, the voltage is 90%. I'm equally supporting 43% of my requirement, reactive power requirement, 43%. If you look at it, the power injected, reactive power injected to the system is very, very high at 0.9 power factor itself. So another constraint which comes from the grid is one is the frequency. If the nominal frequency, if you are pushing the power to the grid, you need to look at the monitor the frequency. When you are pushing the power to the grid, if the frequency is keep on increasing, anyway your PLL will track the frequency and we are pushing the power. But If the load demand is not there, but the generation is more, then frequency keep on it increases. So most of this PV inverter people works on the frequency control. If the frequency crosses that 50.2, the percentage of reduction in power, it will start. Okay, the slope in which it is, the power is going to reduce to support the system stability. Again, I'm talking about the dynamics in the power system, where it is going to support my system stability by changing the values. So you can see that the power generation is going down. Once it is reached that 50.9, immediately it will come out of the loop. So it is not going to pump any more power to the grid. But if the power again at this point, if the power is increasing, power demand is increasing, then the frequency will come down. Up to this point, it is not going to increase the power as what it is reduced. It will be maintaining constant. At one point, it is a 50.05, it comes, it goes back again to the normal power condition. Basically, it's a kind of a hysteresis loop is implemented over here to address the system stability. So normal inverter, present day, if you see that here the panels are connected, 30 kilowatt panels, directly it goes to the 400 volt bus. You can see here, this is the voltage. But by feeding the active reactive power, you can see that the support has been done with the inverter itself, the same structure which is supporting here with the reactive power. Normally it has that the transformer, and then it is feeding normal system. If you see that looking at the diagram, it goes to the DC to AC, and then goes to the transformer and goes to the high voltage line. I'm coming to the point where the Q is 0, power factor is 1, all the inverters are working, and to get that transmission line stability, again VAR compensation, these STATCOM were used initially. Initial days they were using that STATCOM, that has been replaced by each one can support that 0.9, so the entire system complexity is going to come down. So you can see that the lagging and leading can be supported from the inverter itself. Again, another one is P and command will come basically from the control loop. I can change the value. Previous one, it is set with the 0.9, but it can be altered based on the conditions. How much it is going to support? You can see that 0.45 minus side and negative side, positive side 0.45. This is for the leading reactive power curve. So active power, it can support 0.9. At the same time, it can support 0.45 reactive power. So low voltage right through, this is the condition we need to implement for the grid control, grid connected inverter. You see the condition, what it is talks about here is, they talk about 150 millisecond, even if the system is dead short, you no need to remove the inverter from the grid. It has to be still connected to the grid. After 150 millisecond, that 150 millisecond is nothing but 7.5 cycle for 50 hertz. Okay, 7.5 cycle. Even the voltage at the terminal, once it is connected, that suddenly dead fault is happening, dead short, and it goes to the 0 volt. It should not disconnect up to 150 millisecond. After 150 millisecond, the fault clearance, if it happens and goes to 70%, then it should be working normal, and then it should go to that 90% within that limit. Or up to that, you can see that 650 millisecond, it will be stay at the 30%, and then it starts rising. That also normal. So we not to be disconnect the system. Why they talk about this particular low voltage right through is because if I wanted to synchronize one source, basically this is my PV source equivalent, I have put it as one generator. Already my grid is there in the another side. So if I want to connect these two in parallel, I'm checking the conditions, everything, and I'm closing the switch. correct? So all the conditions will be checked and it will be closed. Once it is closed, if I remove, again I need to monitor. It will take 5 to 7 minutes. 5 to 7 minutes. So why this condition is very important? In case of this fault, because the fault clearance time from the relay and coordination system, it takes care within this time. Within this time, if the fault is cleared, I'll be saving my 7 to 8 minutes, 5 to 7 minutes generation of PV. PV generation will be saved. If I remove the inverter at this point, again, sorry, hello? If I remove my inverter from the grid, then I need to wait for 5 to 7 minutes, stability checking and everything, it will happen, and then it will be pushing the power, reconnecting the system. So for that condition, they have given here, it is 150 milliseconds of the voltage up to 650 milliseconds, and then it is keep on rising. This complete process will happen within 1.5 seconds. This is very, very important, critical design control aspects. We have to look at it very much, very clearly. This is only 1.5 seconds. We have to check the system. Now, coming to this anti-islanding. What is that anti-islanding? I have a grid. Okay, so grid, it is connected with the system, grid system, and different loads. I'm putting the different loads. And here again, my PV system, again, you have a PV system, which is generating the power. Generating the power and pushing it to the, sorry, not mentioning clearly about the things. Because of the time constraint, I need to cover up all the things. That's why I'm drawing it in a proper way. Sorry for that. So the power generated current here is a DC current, not AC current, is pushed from the PV inverter and it goes to the generation. If the load requirement is equivalent to I, it takes only the information here is a V and pushing the current here. The power drawn from the source is 0. Under this condition, someone wants to do the maintenance work here. Think of someone wants to do the maintenance work. Suddenly the old line got tripped. But the load has both the R and L, both the L and C. If this circuit makes the tan circuit and oscillation persists for 50 Hertz, which will not be noted by your PV inverter, because at this point it is voltage is sensed and it is given as an input to the system. So under this condition, what it happens is it thinks that the inverter still grid is there, I can push the current. So under that condition, the person who is going to do the work, maintenance work, will get the shock. To avoid that, we need to check this condition. This is called anti-islanding. Once it is system is islanded, we need to remove the system from the unit, from the inverter from the system itself. How normally we do that testing for this particular one is, this is the inverter unit which I am talking about. This is my grid. So S1 is, S3 is closed and S1 is closed. So the grid is present over here. The unit will start by pushing the power. I'll be closing. So the whatever the generation power equal to the load power requirement. So under that condition, I need to check. This case, what we need to incorporate here is to identify this particular condition. How can I identify? So what normally people does is little bit of reactive power they will be adding. After every 2 seconds once, they will add one cycle of change in angle. The change in angle by the PV system, it won't happen in case if the grid is there. If the grid is a big stiff system, the frequency won't alter. If I alter this generator frequency little, that PV generation frequency frequency little bit. So under that condition, I will come to know the grid is there. But if I alter this frequency, that will make that the voltage to die down to the high voltage oscillation to the low voltage. It has to be detected within 2 seconds. If you look at it, the previous slide, this is 1.5 seconds, and here it is less than 2 seconds. The time required for this anti-islanding, effectively, I have only 5 seconds, because I need to check the LVRT in 1.5 seconds, and anti-islanding, I need to find it within 2 seconds. So if I have to do that, the effective time for checking that 0.5 seconds from the 1.5 seconds. That's why we used to do it 2 seconds. Once the little bit variation in frequency, that will cause the changes, and we can identify the anti-islanding in a PV system. So just I thought I'll be showing that one system, inverter system, which I have part of this development, and complete structure we have developed and we have tested for 15 kilowatt. So basically with the NPC topology, no electrolytic capacitor. Initially we were keeping that NGL. DC side, no electrolytic capacitor. Actually DC side we used it, but initial we were thinking of using without electrolytic capacitor, and we started the design using that ESP. This is my power architecture. You can see that the DC side, actually this breaker should not be here. Actually DC side breaker is altogether, it is different. DC breakers are very, very costlier. We cannot use our AC breaker for the DC side. This picture, it's wrong. So you cannot use this picture for any of these things. This is a DC breaker, has to be there. And followed by that 3-level inverter, filter, DC grid side, sensing system, it goes microcontroller and goes to the signal conditioning. Now, this is the control system which we have designed it. Basically, you can see this is my power card where I was talking about the power structure. Basically, inverter structure will come, and the DC bus input side to address the EMI, EMC, we have put that all the EMI, EMC component. And this is solar panel array. It comes to this input card, and from there power card output inductor and capacitor filter card. It goes to that EMI, and then it goes to the relay 1 and relay 2 and fuse. What is that exactly the condition which I was talking about, IEEE 1547 and other numbers? All what it says that in case the redundancy, in case one it is not working, I need to operate it with the other system to disconnect the system. That's why we have used that 2 relays over here. Another one, control card. If you see that the control card, we have made it using a 2 DSP, because in case of one DSP failure, the other will come and make the system to safe shut down. So these are all the requirements comes from the standards. Okay, JTAG communication for the protocol, and here the voltage information and current information from the grid side, it goes here. The control voltage requirement comes here. This is the gating pulses comes from here, and the sense to voltages and current goes to the other side. This is the DC current and DC voltages. We have represented in the different colors. You can see that identifying RYB phases and the DC side with the DC things. Also, it is connected with fan arrangement to cool and other things. The control logic, what we have implemented inside the firmware part and inside the hardware system. So if you see that we check the DC bus voltage, and DC bus voltage indicates my power level variation. So that's where the PI controller, so it gives my PI value. Here I need to multiply with sine omega t. This sine omega t is nothing but my PLL value. PLL gives my sine omega t. So I'm multiplying directly whatever the component is coming over here with the sine omega t. So this is nothing but my reference current. And here the magnitude of the current is varied. So we wanted to control it with the power control. Power, actually this is the power information. Power divided by that voltage factor. and multiplying with the sign. So I get the current to be injected from the system. What is the current to be injected from the PV system at this point? So here the reference grid current is generated. Reference grid current. And here you can see that 0.15 times of 3 omega t into 90 divided by xc. So we wanted to introduce some new control concept for this particular one. Basically, what it happens is the in the grid connected system, the inverter followed by you will have a LC filter. That LC filter, this capacitor is acting as a reactive power source. So basically, to compensate that, we can use it these kind of a current. So this current is also added into the reference. So my inverter compensate this reference for this capacitor. So perfectly, I'll get the unity power factor current at this point. So compensation is done through this component. Now I got the reference current, which is comes out of the DSP. This is basically implemented in DSP, and here it is going to be a PWM signal. So I need to filter out the PWM and making it as a sinusoidal component. I'm using a low pass filter and a DC filter, so it gives out my sinusoidal reference. This is my reference component. Real sensed component is coming over here. These two, if I subtract it, I should get the error component here. That error component will be processed. Error component is processed in the PI controller, generating the pulses. But another component which we have added over here, because in the 3-level inverter, if you see that we have two capacitors are connected, and this two capacitor voltage balance need to be done. Even though if I connected my resistor at this point, the capacitor balance cannot be perfectly achieved. To achieve that, we have taken that the positive bus voltage, this is positive bus voltage, this is negative bus voltage, and then these two are subtracted and added in the error component to compensate that. So this particular component is compared and we got the pulses. This is the basic implementation we have done inside the processor. So I was talking about the sine omega t in the previous slide, sine omega t, which is nothing but my grid voltage reference it comes from. So how did we implement that particular one is, I have a 512 sample which is from the processor. I already preset value from 1 to 0 to 5 on 511. 0 to 511. Already I have a sine table over here. I have to map with the zero crossing. So I start with the zero crossing and I sample it for the first cycle. What is the time? This is T1. Second cycle time. Third cycle time. Up to 10 cycles, we measure the time component. So we used to do that moving average technique over here. So the 10 cycles average time, if I take it divide by 10, if I add it every component, and if I take it that average, that gives my time. This time divided by 512 is my sampling time, which I need to pick for synchronizing the component. Moving average technique, we have used it over here. So this next sample, if it comes T11, it will take the T11th sample and it calculates the frequency. So the moving average, we have used it for the calculation for the PLL technique. So exactly, I was talking about normal reference will be like this. If I add the third harmonic reference in that, I'm getting. So the another way what we have achieved for this particular one is to minimize the DC bus voltage. DC bus voltage can be minimized by using this technique. That's what we have done it over here by injecting the capacitor third harmonic component into the system. The implemented one, you can see that the inverter line to neutral voltage, how much it is coming, everything, the RMS value, because we have done it for the higher voltage side, because we wanted to cater for all other condition. Indian condition 440 volt without transformer we wanted to achieve plus 10%. And you can look at it at the 480 volt AC line to line. This was our grid current which we got it from the system. And you can see that RMS component and the TSD value, which is much higher, lower values, which we got it. For at 400 also we have tested the conditions, the current harmonics, which is less than. So we operated the three level inverter. You can see that the average switching frequency is around 17 kilohertz. So you can see, you can see that average kilohertz is around 17 kilohertz. This is what we got it. Sorry, reference is 10 kilohertz. Yes, correct. So it is a 17 kilohertz, around that value we got it. This is the switching frequency of 17 kilohertz. We operated that inverter. The efficiency of the inverter which we developed, we have calculated over a power rating. It is developed for 15 kilowatt. So up to 4 kilowatt, the efficiency is this much, and below which this comes down. Exactly the inverter structure here. Actually, this is my module, and this is the heatsink, and this is again gate driver for the 3-level inverter. Control card which I was specifying, DSP1 and DSP2. This goes for R phase, this is for B phase, and this is Y, R by B. And this is the thing is from the DC side. And additional communication we have implemented. So those communication here we were wanted to use without electrolytic capacitor, so we have used it. So this is positive bus, my negative bus. This is the middle. Basically, it is a neutral point. And we have used it all the protection and other aspects. So this is the filter card where this is the current sensor. This is a capacitor used in the AC side. Again, this is current sensor, 2 current sensor. For redundancy purpose we have used it. This is for entire system biasing where to be operated. This is basically a 1000 volt input and 24 volt output we will get. Okay. So that kind of a structure with this input side is the EMI component, EMI EMC, and the 2-switch flyback converter is operated. And this is for the AC side EMI EMC. You can see the choke; it is not very clearly visible. And MO we use metal oxide variosters. We have used it. And this is the inductor, and this is the DC side. This is a ground current sensing is also very important. It's a some 5 milliampere or something is the requirement. So for that we have used it, this ground current sensor. So all the current whatever it flows, it should not the difference whatever it is in the positive and negative should not exceed the 5 milliampere. I think I'm not sure about the number. That is the point we need to address on the grid tie inverters. So if you look at it, I have talked about the structure, how and what kind of a control we can implement, midpoint balancing and other things. So my presentation covers all these things. So I have not done about the off grid, but it is there in here. It is not off grid. So only grid tie inverter I have concluded from my things. Thanks, and I would like to acknowledge one of my PhD student Rupa and Venkat Raman. Venkat Raman is presently in assistant professor in Delhi Technical University. Rupa is currently she is going to submit the thesis. So those people also part of this work, and I want to acknowledge them. And the data is collected from that SMA inverter portal. And that's all about my presentation today. If you guys wants to ask the question, the floor is open.
Yes, sir. Hello, sir. Thank you so much for the informative presentation.
Yeah.
And few participants are having few queries, which I am posting in your chat box, sir.
Okay.
Yeah.
Why the first question is I'll read the question and then I'll do it. Why the efficiency of the panel is very low and how it can be improved. So this is basically the material property which we are getting it from the panel manufacturer. As an electrical engineer, we try to maximize only the electronic system which is connected with the panel, we are trying to maximize the efficiency, so that at least I will get the panel efficiency. So the panel efficiency can be improved by only the manufacturer material used. So material science one. Okay, I don't have any other information about that particular one, but if I make it my electronics is 100%, so I can use it my panel is completely. That is the first thing. Second one, what is the impact on current generation and temperature if the gallium nitride semiconductor instead of conventional silicon based semiconductor in PV cells? So again, it is a material based question. If you are using a gallium nitride material, the material property is going to be different. Okay, so I'm not expert in material things. I'll not be able to comment much on this particular one. But normal gallium nitride devices, if you are talking about the power electronics point of view, if you are using it, the efficiency are going to be improved. At the same time, you will get the power output is more. That's the only thing. How the cell temperature is different from the ambient temperature. See, one thing is the efficiency of the cell is 17%. I talked about. What is that 17%? That means the original cell efficiency is 17%. The original power is multiply with that, right? So if I have that much power, where that power is gone, you can see that you put the only the silicon cell and touch the temperature, because already the panel is covered with the glass, tough glass. If you touch that glass also, the temperature is going to be more. Okay, so the temperature inside that cells are going to be increased because of the power generation, and the losses happens in the around that. So that's why the temperature is different from the ambient temperature. You can check it. If you have a panel, backside of the panel, you can put your hand and check that the temperature and ambient temperature. That will give the clearly what is the difference between these two. How cell temperature different from the ambient? That's over. What are the possible issues we face when PV synchronizing to the grid? So first thing is the grid synchronization. The PLL concept need to be very thoroughly understand, and then we have to do that. Because if you do that without synchronizing, if you are trying to push more unaligned way, basically there's without synchronizing, if you are pushing the power angle changes will happen, and the phase difference is one, and the frequency, you think of your frequency is 51. Worst case I'm talking about. I'm not talking about any reality which will happen. If at all, if your frequency is 51 and your grid frequency is 50, what will happen? There is no power flow will happen. Okay, it will dump the power into the capacitor. The capacitor will go to the over voltage mode. So make sure that when you wanted to connect the grid, first when it is connected to the grid, don't push the power immediately. You wait and watch the DC bus capacitor, how much it is growing up, and then whether it is completely synchronized, then you start the current injection. Can we use the capacitor bank for mentioned in this maintain? See, yes, capacitor banks only will be used because the values are different for the different things. Okay, and some more questions. Can we use the capacitor bank maintaining
Sir, that question 5 is the same. Sir, the question 5 is the same. Yeah.
I've not.
Okay, sir.
Yeah, got it. So somebody was asking, the question is, can we use the capacitor bank to maintain a constant voltage across the panel when the voltage drops in a partial change? So if you are trying to use the capacitor at that point, the problem is your capacitor cost is increasing. And once you started using the capacitor, your MPPT point will be lost. Okay, so you have to make sure that the capacitor value in an optimum way. But in case if you are trying to do the MPPT in boost converter, the capacitor value is immaterial. Okay, capacitor value is immaterial because we have done the transfer function analysis for that one, and that capacitor, because of the boost converter, continuous current is flowing either in the switch side or capacitor side. This capacitor will not come into the picture. If you put a heavy capacitor also, there is no use. Okay, so that will impact my MPPT point. What are the features in nano inverters? Actually, the material science is very much growing. The MOSFET and other things, whatever we are talking about, the fab level itself, in the cell itself, they wanted to incorporate. Backside of the cell, they wanted to do that. That is more towards the device physics point of view, and also the PV manufacturer point of view. If I look at it, the hope for power electronics engineer, if he overlap with the materials engineer, and it can be done. Okay, so nano inverters, it is going into the materials point of view. How does the solar cell feed the uninterrupted power supply to the grid? Is bad weather condition. Solar cell feed the uninterrupted power to grid. Bad weather condition. Actually, the bad weather condition, definitely the solar will not feed any power to the grid. Okay, uninterrupted means I'm not getting the question itself. If I'm right, the power generation will go down. Solar, if it is a shading condition happens, power level will go down. If your load demand is more, it will take it from the grid under that condition. Can we use the 3-level inverter instead of 2-level inverter? What will be the changes? If you use that 3-level inverter, so first you have to look at it, the power level. If the power level is very high and you wanted to reduce the switching losses, you can use the 3-level inverter. Okay, so 3-level inverter, presently it is used for all string inverters is with the 3-level inverters only. And also I have seen that PMSM based wind generation also uses the 3-level inverter. So basically the advantage of using the 3-level inverter, I have a minimal harmonics. Okay, the harmonics will be minimal, and the EMI EMC point of view, I can address it very easily. EMI EMC points. Can it possible to connect direct inverter to the residential grid without using the transformer? By using the boost converter, it is possible to maintain the voltage level. Any disadvantage? So whatever I spoke to the system, without using the transformer, we wanted to do that. Okay, so the transformer, without using the transformer also it is possible. The front side, there is a boost converter. The meaning is, if the boost converter is able to support the DC bus at the worst condition, you can do it. Otherwise, you have to use some isolated topology, that is a high frequency transformer at the DC bus side. There is no harm in it using the boost converter followed by the inverter connecting to the grid. But only condition, the boost converter should not be stressed out. What will be the effect of DC voltage is left float in the inverter side? What will be the effect of DC voltage is left floating on the no, actually what condition says that is, any unit is, once it is switched off, within 5 seconds, if you see that the safety procedure, any of the inverter, UPS inverter or anything, the sticker will be there. Switch off and wait for 5 minutes or 5 seconds, and then you touch the thing. So that 5 seconds is nothing but the capacitor dischargeal time. So capacitor will discharge within that time. So you have to make sure that, that's where I told that the capacitors are connected parallel with a high watts resistors, so that high value of resistor. So once the system is switched off, immediately the discharge will happen. Okay, so at present these are all the questions. Just I wanted to show one more thing. I switched on my camera. I'm closing. Stop presenting. Yes, I turned on my camera. I hope you guys are able to see the camera, right?
Yes, sir, we can see that.
Yeah, I'm holding an inverter. It is a intelligent power module based. You can see it in my hand. I'm not able to see my screen, so just
we can see it, sir.
Yeah. So it's not coming in my screen. So that's
Yeah,
why
we are
just
able
one
to see it,
second.
sir. Yeah.
Yeah. So okay, yeah, in the top corner, I'm able to see that. So this is the inverter which we have developed right now. It is for 2 kilowatt system, which I'm handling in my one hand. You can see that. So somebody was asking the capacitor bank here, capacitor bank. I was talking about that high voltage resistors, which are there, okay, which are there here. And the module you can see, I don't know whether it is visible in the camera, in between the heat sinks into that board. Okay, so this is
Yes,
the
yes, sir.
design. Presently, we have done it, and it is fabricated. So this is the intelligent power module, and here this is R phase RYB, and this is for the neutral, because here it is a 2-level inverter, but still I have a neutral point between these two capacitor midpoint. If I take it, I can use it as a neutral. That's what the neutral point is here. This is the positive terminal. This sorry, this is the for control supply, voltage supply. This is the positive and negative. Okay, so this is our own baby kind of a thing. So what we develop everything, and then we give it to the people to manufacture and give. So that has been done for this particular case. This is controlled. You can see here there is a two rows of connectors. Exactly, if you look at it, TMS 320F the Piccolo processor from the TI. That is the processor we are going to directly. So just I thought I'll show this development in-house. Thank you.
Thank you, sir.
Yeah.
Yeah, thank you, sir, for such an excellent and informative session on control of grid-connected PV inverters. Basically, it started from the basics to the design and applications of PV systems in on-grid and off-grid. I think all the participants enjoyed the session. And once again, we would like to express our heartfelt thanks, sir, for accepting our invitation to give a expert lecture on this
Thank you.
STPP. Thank you so much, sir.
Thank you. Bye
Yeah,
bye.
thank you, sir. Yeah, yes, sir. Bye, sir.
Thank you, dear participants. Now, the next session, or the third day, will be taken by Dr. Asarani and Professor Nalin Bihari Dev Chaudhary. So we'll start the next session in 5 minutes by 11:45. Thank you. अभी तुमने ना होगा ये था ना ये होता एक बार देखो इसको ऐसे ही रखना है वो आ गया स्क्रीन पे देखो इसको मिनिमाइज मत करना हाँ ठीक माइक Welcome, welcome, sir. Shall I start, sir?
Yes, yes.
Okay.
Yes, sir.
Good morning, dear participants. Now we are entering into the second session of third day of the 1 week STTP. And now we have two experts from NIT Silchar, Professor Nalin Bihari Dev Chaudhary, sir, and Dr. Asarani MA with us, who are handling this session on microgrids and control of grid-connected wind generators. Heartily welcome, Sharan Madam. It is my privilege and honor to first of all introduce Professor Nalin Bihari Dev Chaudhary, sir, Professor, Department of Electrical Energy, Engineering, NIT Silchar, in this 1 week SCTP. Dr. N.B. Dev Chaudhary graduated in Electrical Engineering from Assam Engineering College under Guwahati University in the year 1994, and Master from IIT Kanpur and PhD in 2011 from Jadavpur University, Kolkata. He has served 23 years of vast experience in teaching and served in different administrative capabilities, including deans, heads, faculty in charge, members of several doctoral committees, etc. He has more than 60 publications in his account, which includes 39 publications in the international journals, IEEE Access, International Journal of Electrical Power Energy, etc. Under his eminent guidance, 4 students completed PhD, 7 scholars are pursuing PhD now. He is a renowned academician and researcher who have provided many significant contributions in the area of deregulated power system economy, distributed generation, power policies, reliability of power system, integration of renewable energy, etc. Then about the next expert, Dr. Asarani AMA, who is handling the session. He's serving as the assistant professor in the Department of Electrical Engineering in NIT Silchar. Dr. Asarani did his BTech from College of Engineering, Kerala, the Spedus on MTech in Industrial Drives from Rajiv Gandhi Institute of Technology, Kottayam, PhD from NIT Trichy in 2016. She has 11 years of experience, which includes academic and industrial experience. Before joining NIT Silchar, she worked with Fluid Control Research Institute, Palakkad, Kerala, Ministry of Heavy Industries, Government of India as a JRF and Assistant Training Coordinator. Later lives Believer Church, Karamal Engineering College, Kerala from 2004 to 2017. And later she worked with other colleges as a senior assistant professor. She has more than 14 publications in her accounts, including transactions, this IET electrical power. She has applied for a patent. So she has provided many significant contributions in the area of grid integration and control of wind generator under distorted grid conditions, especially. So I now request first Professor Nalin sir to start the session. Thereafter, session will take over by Asrani. Sir, please.
Hello, good morning, everyone. Am I audible?
Yeah, it's fine, sir.
Okay. The participants, we have already learned many related issues from the power electronics earlier in all earlier sessions. Here, specific field is left in the smart grid where power electronics components are extensively used. Here, the smart grid actually contains many of the field, including communication protocols, bidirectional communication, sensors, measuring instruments, Internet of Things, many other related issues. But whenever we talk about the smart grid and we talk about the integration of green energy like solar and wind, then certainly the power electronic equipments are coming into picture. Here, this particular session related to smart grid and wind energy integration is divided specifically in 2 sessions here under the same session. The smart grid portion and its use of power electronics will be discussed by me, and the other portion, the power electronic applications and integration of wind energy to the smart grid, will be handled by Dr. Asarani MA. First, we'll talk about the smart grid. Whenever we talk about smart grid, the word smart coming into picture. If you see the slides, what is a smart? Why we call a grid to be smart? Let us see the word passive. If we say passive, then it can communicate only when required, like passive RFID or QR codes. Whenever we talk a system is active, then it can communicate whenever needed. When the system requires, then it can communicate. Then the system is considered to be active. The third word is aware. When as action-based the simple computation can be done by the system, then the system is considered to be an aware system, where such type of system is having around 5 senses maximum. For example, we can see the telehealth. Such type of related systems are considered to be aware system, means they can take decisions little bit but not much, and they can communicate and do a simple computation on the basis of data accumulated. Now the fourth one is the autonomous. The word meaning is it can make decisions based on rules, where we have like autonomous cars or smart grid. Like a human, whenever we get the opportunity and we get the senses, then the human can take a decision on the basis of the input. Similarly, if a grid can sense the senses and take decisions of its own, then certainly such type of grid can be considered as a smart grid, just like a human. Now we'll go ahead with the concept of smart grid. Then what was the earlier grid where we had, if you see the figure here, the sustainability change in preference. Here I will use one highlighter and quickly show you. This is today's electricity, what we have. Here we have the generation, transmission, and distribution in a hierarchical manner, starting from the generation. From the generation, we have transmission. From the transmission, we have distribution. Then we have from secondary distribution, it reaches to our home, to household, means to customer. In this electricity, the things are the problems related to electrical problems are not addressed by the grid itself. Here, this is our today's electricity. If we talk about the smart grid, then what happens? We have the generation, we have the customers. These customers may have access to different sources of power, like the customer may have his own solar power, he may have his wind farms connected to him. Now, another issue, each and every stage in a smart grid, there must be some sensors. The sensor will sense what? The quality of power, time of use, amount of power, type of power, then it will communicate to its server. This communication, in most of the cases in smart grid for a home level, where we talk about HAN, home area network, mostly we use ZigBee or 6LoWPAN protocol for communication in between sensor and to the server. If in a locality there are n numbers of houses available, then certainly the data gathered from each and every sensor from a house will be stored, and then we will call the total area of those households in that area to be neighborhood area network, NAN. From this NAN, for different sensors, we will sense the type of electricity used, amount of electricity, and all these related features they will collect from each and every point. It will send to the server. Then the server will store the data in cloud. Whenever we talk about smart grid, certainly few specific buzzwords coming into picture. One is Internet of Things and another is cloud computing. In this particular workshop, we are not much digging about these particular two words, including communication protocols. In smart grid specifically, if we talk total working of a smart grid, certainly we need to discuss about its communication protocols. And then we talk about Internet of Things, then we talk about cloud computing. Here, in this particular session, we are not dealing with all those specific topics, but however, how a power electronic device is used and where is the necessity of use of power electronic device in smart grid, we will concentrate mostly on that particular issue. Therefore, a tomorrow's choice will be whenever all these network parameters, all the network components are connected to each other and communicate through them. Now we'll go ahead with the next slide. What is smart grid? We have already discussed what is smart grid, but I have written few things from here. The diagrams are here. It may be a computer, it may be a meter, it may be a laboratory equipment, it may be your solar power, it may be your vehicle charging, another may be your wind power. All these are connected all together and communicating each other. The smart grid integrates information technology and advances communications into the power system in order to increase system efficiency and cost effectiveness That is number one. Number two, it provides customer tool to manage energy use. Another one is the improve reliability, resiliency, and the power quality. This word, improve reliability, resiliency, and power quality, means the smart grid offers to go much deeper related to smart grid. This particular session, we are not talking about reliability, resiliency, and power quality. Here specifically, we will be talking about where the power electronic equipments are used in smart grid later on. But before that, we must talk about the smart grid and what is smart grid. Until and unless we don't understand what is smart grid and what is the need of smart grid in today's era, then it will be very difficult to understand what to use and where to use. That's why in the beginning, we have discussed about little bit about smart grid. Next, it enables the use of innovative technologies, including renewable storage and electric vehicles. At this point of time, though we are talking about the word innovative technology, here the innovation means in renewable and storage, specifically the new generation electronics and the communication advancement actually connects all the renewable powers and its storage to deliver its data and take a decision to a handheld device. Therefore, the innovative technology and its advancement actually brings all those equipments which are located far, actually combines all together in a single device from which you can quickly control and look into it in a handheld device through using apps. Similarly, the electric vehicle, its charging, discharging, state of charge, type of charge, then how much it will go with the charge, when we'll get the available power, all these related issues are also are also available in a handheld device or fitted with the vehicle itself. Therefore, the advancement of communication technology and its different protocols these days actually combines the use of power, including generation, transmission, and distribution. This particular work of power, earlier in the conventional power system, we do not have such facility. But in using smart grid, in general, we have the facility to look into and take a decision on the basis of the data information from each and every point, and it enables us to take a decision after analyzing the data properly. Now we'll go ahead to the next slide. Now, in why we need the smart grid? Here in smart grid, we have few equipments. Whenever we try to implement smart grid, we have some challenges. And certainly whenever I talk about the implementation of smart grid, certainly we'll get some benefits. Here, it increases the access to electricity. Then it reduces transmission and distribution losses. It improves reliability and quality of supply. Smart grid also ensures energy security. Smart grid meets demand and manages the peak load. Smart grid also identifies the aging and overstressed infrastructure and the equipment well in advance. Smart grid integrates the renewable energy quickly. Smart grid offers also safety and sustainability to the system. If smart grid offers such a bouquet of diverse amenities, then what are the challenges to get all those facilities in the smart grid? The challenges are high system loading on large network. If the network is very large, then it offers system loading, very high system loading. Next is fluctuating renewables. Renewable energies are not fixed, just like a hydrothermal or thermal or any other conventional power plants, like other conventional power plants. The renewable powers are not fixed. They're not delivering the fixed power because it depends on environmental and all other climatic issues, like say, a solar power plant or a wind power plant or wind power farm. Though it is installed for a specific capacity, but due to the environmental and climatic conditions, the power delivered by that plant is fluctuating. Therefore, to know in advance about what will be the power injection, how much will be the power to be delivered by the plant well in advance by using the IoT devices and through smart grid, then it gives a better idea for the power engineers and the planners to take appropriate measures beforehand. This is one challenge. Another one is the new consumption model, like electric vehicles, smart buildings, and rooftop solar. These are new models coming up for buildings and vehicles. Whenever we are using these new models of power producer or power consumption, then certainly we need to take care of these issues. Like a small example, if you take like electric vehicle, if you want to travel around 500 kilometers from your hometown to another place, then what happens? Your battery charge for that electric vehicle may not be sufficient to run for 500 kilometers. In between, you need to charge your battery in between in charging stations. It is just like a mobile network. If you see, if you have a mobile, if you are talking from one city, then you are traveling to another city, then you are traveling to another city, the mobile rates are different. Means in on net, if you are calling to a home network, then certainly the rates are different. And if you are calling from the other network, rates are different. Similarly, if you are drawing power from one network, the price of the power will be different at different time slots. Like in peak hours, the price of the power is different, and in off-peak hours, price of the power is different. If you are charging your vehicle in off-peak hours, certainly you are paying less amount for your charging. But if you are charging your battery vehicle of the battery during peak hours, then certainly your charging price will be more. Another issue in battery is that if your battery is fully charged, or the load in the network is very high, demand is high, then certainly you can connect your battery to supply the power to the grid. Means in this context, we can say that you are taking power from grid to battery during charging, or whenever you can you feel that you don't need the power at this point of time and you have fully charged battery, you can sell that power to the grid again when the grid needs to cater more demand. That means grid need to identify for that vehicle it is charging or discharging. If you are charging, then you are paying. If you are discharging, then you will be paid from the grid. Means this particular issue should be taken care by the smart devices using IoT. Why IoT? Because a vehicle is not stationed only at a single place. It may move from one place to another. Therefore, if we connect this particular vehicle or the battery to some smart devices in such a manner that it can communicate the status of its battery as well as it is charging or discharging, in all these phenomena are recorded and transferred to a data center, then when quickly we can monitor all these issues, then it then a smart vehicle or an electric vehicle can be used as a consumer as well as the supplier. This is one challenge when we talk about fully smart network. Then a smart network should have capability to identify the type of power, time of use, and all other related issues through the smart devices. Another challenge is the centralized and decentralized generation. Some generation stations, they do not generate continuously for all the time in 365 days and 24 by 7. Some generating stations, they are intermittent in nature. Like, take an example of green energy. A green energy, in general, we do not use continuously to the grid. Means sometimes if you are connected with a rooftop solar, if for continuously 5 to 7 days it's raining, then certainly your rooftop solar cannot satisfy it can your own demand. If you connect this rooftop solar to the grid, whenever you have it means you are generating more power through the solar, you can sell it to grid. Whenever there is no power produced by this rooftop solar, you can get it from the grid. Ultimately, what happens? This rooftop solar is a decentralized generation. Whenever necessary, it can collect power from the grid, or whenever it has excess power, it can sell to the grid. These are the challenges we need to face whenever we talk about the smart energy or smart grid. Another challenge is increase the energy trading. Energy trading is increased many folds in last few decades. Therefore, for proper energy trading, it is necessary to identify the different point of access from generation to transmission to distribution and to customer. Therefore, to identify the amount and time of energy, it is necessary to integrate that grid and consider and upgrade this particular grid to smart grid, which will help us to identify all these different problems, and we can take adequate measures for that. Another is lack of awareness it is a challenge for us because lack of awareness. The apparatus and equipments are available in the market. If I fit it in a particular smart building to make it a smart home, if we are not aware about what are the equipments and how it works, then it will be very difficult for the user to identify to identify its consumption. And during the peak loading period, if it is necessary to be shut down few of the apparatus which are not used and necessary to be used during that time, those decisions should be taken. There are two issues: a human can take a decision by which own, or otherwise the system can take decision. If you preset the value for such apparatus which can be shut down for some time to save energy in during peak hours, that decision also can be taken automatically by a smart grid apparatus. Now, what are the benefits of smart grid? The improvement of efficiency. Already we have told the improvement of efficiency, the quicker restoration, reduce OM and cost, then peak demand shifting, then reduce the pricing, increase the renewable integration. Here we mostly concentrate on the renewable integration in the latter part. Now, another benefit is the multiple energy choices to the end of customer. Another benefit is prosumer. Prosumer means producer and consumer. A Already I have given an example. If you have a rooftop solar, whenever you are having more power, you no need that much. You don't need that much of power to be consumed locally. Then certainly you can sell this power. Means you will be a producer. Otherwise, whenever you are not generating required power, your house is connected, means system is connected to the grid, you are consuming some power, then ultimately consumer plus producer, a new word coming up, that is the prosumer. Then we can increase the number of prosumers. Another is improve the security, and many more benefits we'll get from smart grid if the grid is really smart. And a small idea about the transformation of information enable then highly interconnected network between electricity consumers and suppliers. That is, earlier we had limited choice. Now in smart grid we have more choice. In normal grid we had one-way communication. In smart grid we have two-way communication. In normal grid we have very few sensors. Now we have pervasive monitoring, means many sensors are connected in each and every point and monitor. Earlier we had in normal grid we have analog control. Now in smart grid we use digital control. In earlier normal grid we are having reactive maintenance. Whenever the system is not working, then we will start working and find out its maintenance. Now in smart grid, the condition-based maintenance. Automatically, the smart grid and other apparatus will identify the area where the maintenance is necessary. Means the preventive maintenance is done in smart grid. Or earlier, the system was blind to all its problems. Now, in smart grid, the process is self-healing. Automatically, it will try to restore to its normalcy. Now we'll go to the next slide. That is a smart grid again. The electricity network. The smart grid is an intelligent electricity network. Why we term it to be intelligent? Because it has the capacity of self-healing, monitor, control. Everything is done automatically in the smart grid by using Internet of Things, Internet, and computing and computational devices. Therefore, this is called an intelligent electricity network. The smart grid in general works on load balancing, accident prevention, thief detection, reduce power and revenue losses, and two-way information flow like electricity and information. altogether flows in real time. The next generation power grid is based on evolution of communication and networking infrastructure integrated in electrical grid, enhancing data exchange and automated management power system. What does it mean from this sentence? We understand that the communication technology improves a lot in the last few decades, including mobile connection from 2G to 3G to 4G, now it is 5G. Now, using the advancement of communication technology, we can quickly get the data from one place to another. We can transfer data from one point to another very efficiently. Therefore, with the innovation of and evolution of communication networking infrastructure, it is very easy to monitor and take control of the whole power generation process, including consumption. The communication network should be able to meet the specific and need of the power grid. That is, the communication network should have a flexibility, resilience, sustainability, scalability, and cost effectiveness, interoperability, and interaction of the participating entities. Here, interaction of the participating entities, we are talking about the generation, transmission, distribution, aggregator, market player. All these are different participating entities in a grid. Thus, the name of smart grids is entitled to the next generation power distribution network. The president, Pacific Gas and Electricity USA, Chris Jones, once told in his expression in one of his lecture that the grid will soon be emerged as grid of things. Which grid? That electricity grid. He resembles the word, like how the internet evolving as internet of everything or internet of things. Then certainly one day it will be a grid of things. That is, evolving smart grid will be a grid of things. Earlier we had the traditional grid, now it will transfer to smart grid. That means the evolving smart grid of the 21st century will drastically different. What we have seen the electrical grid today, after implementation of all the smart grid components with all the available communication protocols, the 21st century electrical grid will be completely different. Now, we had electrical infrastructure, generation, control, transmission, distribution, then the consumer. Similarly, if the electrical energy flows from one point to another in this direction, certainly the information also flows from one point to another through communication network. Means the generation will get the sense of how much it is generating, then it will sense, it will communicate to the data center, data is stored, it will get the data from other renewable energy sources, from solar and wind. Then all this data can be processed. It is connected to the consumer and data center. Then all these data points are all connected all together, and ultimately the information flow and the electricity flow works together in a smart grid. Now, the electricity supply, starting from the generation to transmission to distribution to the consumer, was a serial fashion earlier. In a serial fashion. Now, when we consider it to be a smart grid, a consumer may be a producer if he has his own facility for rooftop solar and wind. Therefore, the information flows from the consumer to distribution, transmission, and to generation. Informations are coming from each and every point. Means all they are connected through information. Already they are connected through electricity network. Now, for information point of view also, each and every one is connected to each other. Therefore, the supply chain is not serial, it is a circular one. Now I'll go ahead. Now we talk about smart grid, and smart grid. In smart grid, there are many components available. Like we consider it to be a smart generation. Instead of generation, now we will term it to be a smart generation, which will optimize the energy generation based on the feedback. The generator will not generate blindly. Number two, we'll talk about instead of substation, we use the smart substation. Means it will monitor and control the substation from remote location. Transmission distribution, it was a completely passive earlier, except with some relays and fault detection and protection. Now we'll consider it to be smart. That means it builds the self-healing capability to computer-aided control decisions. Each and every consumer is having the energy meter. Now that energy meter will consider to be a smart energy meter, which will enable two-way communication between the consumer and the supplier. And the appliances, what we have at the consumer point also are having the capability of smart appliances. That is to build the capability to decide an ideal time to consume power. Like in general, we use all our appliances as per our wish without knowing the price of electricity at that particular time. Therefore, if we know the price of electricity, means all these transmission, generation, substation, transmission, distribution are all connected to only one network, then certainly a appliance like your washing machine will try to find out its slot to operate in such a manner that the price of electricity is low, means in off-peak hours. Then such type of appliance will term it to be smart appliances. Means in a smart grid, starting from the consumer point, if you see they have smart appliances, they have connected to smart meters. These are connected to smart transmission distribution system, then the smart substations, the smart generation. Then the next slide we will see a smart grid will be a completely smart in sense that the participating entities like energy provider, policy maker, regulatory authorities and enterprises. And similarly, the power grid parts, generation, transmission, distribution and customer, all are internally connected through communication network in such a manner that they can take decisions of their own automatically. Renewable, non-renewable, transmission, substation, house area network, BAN, IAN means the area network, the neighborhood area network for all the industrial area network. For all these are connected. AMI is advanced metering interface in such a manner, and the communications are from the market, from the operation, from the service provider. Then certainly they are all connected to under a communication network, and they can take decisions in such a manner. Why we need all these communications? Because to reduce the peak load, to flat the peak load, so that a few of the appliances can be shifted from peak load to off-peak loads. Now, if we talk about the smart grid infrastructure, this is a very important diagram. It is a model. The smart grid architecture model developed in environment info. Here it is showing the domains. Domains are generation, transmission, distribution, customer premises, the different zones, the process, field, station, operation, and different layers, different interoperability dimensions, with the component layer, then communication layer, then information layer. Means in component we have these components, smart components. They will collect the data, then they will communicate. From the communication, they will store the data in the information. Then after storing the data, the meaningful information and the processing of data is in the function layer. And once we get the meaningful data, then in the business layer it will be analyzed, and accordingly it will be implemented. Therefore, this particular diagram in generally used in smart grid architecture, where all these different operations, different zones, and our interoperability dimensions are shown in a single diagram. Now, what is the need of smart grid architecture and design framework? Here we have advanced metering interface for residential. Then we have peak load management, which is a part of smart grid. Another is outage management, is a part of smart grid. The power quality. Here in this particular discussion, we will mostly talk on renewable integration instead of all this. It will take much more time. Some other day we'll discuss, but here we will mostly concentrate on the renewable integration model in our next slide. This is the need for smart grid architecture and design framework. Now, renewable integration in smart grid. Why we need it? To reduce carbon emission and emission of other air pollutants and to promote green energy. We need renewable integration specifically for reduce carbon footprint and promotes green energy. Thereby, it enhances the reliability of the transmission, the electricity network. It improves the security and resiliency. It also supports the reduction of oil use for plug-in vehicles. Whenever you integrate the renewable energy, a self-sustainable model is already developed because of this integration. Now, how we will integrate? Whenever we use, now already we have discussed that the renewable energies are fluctuating in nature. Therefore, according to its generation, if we try to integrate the renewable energy to the grid, certainly we need some power electronic devices, inverters and converters, to be connected to it so that it can connect to grid through this converter and inverter. Or in sometimes we have direct to grid connection also. In our next two slides, we'll see a simple schematic for integration. Like we have wind, solar PV, or maybe UPS. These are connected to these inverter converter combinations. This is distributed load, which is connected to the static switches, to the point of common coupling, to the grid. These related issues of converter and inverter and its different configurations and topologies, the next presenter, Dr. Asarani, will explain you in a better manner from this point. We have another slide, then we will sign off. This is the integration structure in general. The first one, we have a full-scale power electronics model. Full-scale power electronics model means we have wind power. So filter, AC-DC converter, DC to AC converter, then we have filter and connected to the transformer and through the grid. Here it is the full-scale power electronics is used in one model. Next one is partial scale. Partial scale means we have a DFIG, WFI induction generator, which is directly connected to the three-winding transformers and connected to the grid. And we have another parallel lines, which we have the AC-DC converter, the AC converter, and filter, and connected to the three-wind transformer and to grid, where the power generated by the wind can be fed directly as well as through power electronic devices. That's why we are using the word the partial scale power electronics. Now I'll stop here. You have few references and important links for this, what we have discussed earlier related to smart grid. If you're much more interested, you can be in touch with me later on. Thank you very much.
You can sit. Yeah. Good afternoon, participants. Can you hear me? Yeah. So now I think from Sir's presentation, Nalin Sir's presentation, definitely you would have got a flavor of what is smart grid, what are the different topologies, like what is microgrid, what is a need. I think everything you got to know. So now, as the second part of the session, let us see what is the like how are we going to control grid connected wind generators. So basically the overview of the presentation, what I arrange is like this. It includes a type of wind energy conversion system, schematic diagram of the DFIG system, because why DFIG system is mentioned is like it is most popular and used like nowadays everywhere because of the efficiency. For that details I'll come into. Then effects of voltage sag on DFIG, then what are the synchronization techniques, because morning session even I have seen like few participants were asking about what is synchronization, so that is also involved in this, and how it can be controlled, generator can be controlled under balance and distorted grid conditions, both we will be discussing. So before going to the details, as an introduction, like as already Nalin sir has given a very good introduction and a flavor of what is smart grid and everything. So there you would have listened like this renewable energy sources are increasingly popular because of the increasing demand of electric power. And as we know that the other non-renewable sources are fast depleting and the renewable energy sources are only continuously replenished. And as we know, the major source of renewable energy is wind and solar. And you would have heard so much about solar in for the past 2 days, like different type of topologies, controls, and everything. So actually, this is the data which I have taken from the MNRE website, Ministry of New and Renewable Energy. So out of the total installed capacity in India, 23.9% of the contribution is from it is not coming. It was not coming. It was not coming. Super. Yeah, can you see the screen now? Can you see the screen now? Okay. Yeah, even just I started only. This was the first slide which I put. It was about the overview of the presentation. I think you have heard that. Yeah, then just I entered into the introduction only. So where I was saying about like the total contribution of renewable energy. So out of the total installed capacity in India, if you're calling it as 100%, 23.9% is from renewable energy sources. So you can see that what is the like drift which is happening from even within a year. So in June 2019, we can see that it is almost 125 gigawatts is the renewable installed capacity in India. By March 2020, it reached almost to 135 gigawatts. So it is actually number is getting the effect of renewable energy integration with the grid is increasing on a larger scale. And if you are further seeing to the minute details of this renewable installed capacity, you can see that solar is actually contributing to almost like 9.9 gigawatts, whereas wind is actually 11.1 gigawatts, and remaining is the contribution from biomass and small hydro. So this is actually about what we are calling from this 23.9%. And now we can see that the government is further targeting to increase the installed capacity by 178 gigawatts by 2022, out of which 100 gigawatt will be from solar, 60 from wind, and remaining will be from biomass and small hydro projects. So as we are telling, no, it is not so easy to just like that integrate the renewable sources with the grid. So we know that when we are integrating the renewable sources with the grid, it involves power electronic controllers. So if you're talking about, since the session is about the microgrids, if you're talking about the microgrids, we know that microgrids or this microgrid means like the distributed generating sources, you will be integrating with the conventional grid, correct? So what happens is when more and more renewable sources are getting integrated with the grid, that time you will be having frequency variations, because as you are integrating more and more, or when you are tapping more and more load, there will be deviation in the alternator speed. So that will lead to frequency variations, and because of this load change, definitely there will be voltage fluctuations also. So these things have to be taken care of when we are integrating more and more sources with the grid. So let us see what are the types of wind energy conversion systems available. So basically, wind energy conversion system, or they are classified as fixed speed wind energy conversion system and variable speed wind energy conversion system. So in fixed speed wind energy conversion system, we can see basically that is about, or the device it is actually about the squirrel gauge induction generators. So basically, when we are talking about the squirrel gauge induction generators are devices which are actually coming under a slip of, or which they will be generally operating with an operating slip of plus or minus 10% only. Okay, so generally these devices, or the normal directly grid connected induction generators, will be operating at a slip of plus or minus 10% only. So the meaning of fixed speed is basically this is the characteristics of a wind turbine. So this is nothing but the power versus wind velocity or the speed characteristics. So I can subdivide the characteristics into two. So this part is nothing but which is called as the MPPT region, so as how we are talking about the same thing in solar, and the remaining part, this much actually is the constant power region. Okay, so this is the constant power region. So what happens here is, since this is a fixed speed machine, this machine cannot use the opportunity of extracting power from this MPPT region. So generally fixed speed machines will be operating only in the constant power mode. So that is a disadvantage. So what happens now? Like this is actually the characteristics of a turbine, which is provided by the manufacturer when we are buying wind turbine. So there we can see that for each wind velocity, so if it is 8 meters per second, this can be the maximum power which can be extracted from that. If it is 10 meters per second is a wind velocity, this you can extract, and this you can extract, like that. So actually how the power curve is coming is actually by joining all these things. Okay, so that is the power curve what you are getting. So this region cannot be used in the case of fixed speed wind energy conversion system. Only this part can be used. So whereas when you're talking about the variable speed wind energy conversion system, we can, there also SEIG is there, but with a different configuration. And we have permanent magnet synchronous generator, and we have doubly fed induction generators also. Okay, so now let us see one by one fixed speed wind energy conversion systems. So fixed speed wind energy conversion system. So fixed speed wind energy conversion systems are basically grid connected induction generators. Okay, so they are grid connected induction generators, as I told you earlier. So grid connected induction generators are basically having the advantage of, as we can see that. So this is a fixed speed wind energy conversion system. So in a fixed speed wind energy conversion system, as I told you, a squirrel gauge induction generator is a machine which is connected. You can see it is directly connected to the grid. So you can see here there is capacitor bank. So the role of the capacitor bank is to provide the reactive power support needed for the machine, because when a squirrel gauge induction generator is operating, or when any induction generator is operating, it needs actually reactive power, or it needs actually the magnetic flux inside the machine. So you, as we all know that whenever the rotor is rotating and when it cuts the magnetic flux, then only an EMF will be induced here. And then only with the help of that EMF, the power can be pumped from here to there. And morning I have seen like some participants are asking some queries, like how the power is pumping when the grid this side and this side is having same voltage. Actually, how it is done is, generally you would have seen in the equivalent circuit of a induction generator, we are mentioning about the induced EMF inside. Yes or no? So let us say if this is the resistance, this is here, and here you will be having a magnetizing branch. Across this, we will be generally mentioning the induced EMF. Yes. So this induced EMF, okay. So as per the basic fundamental things what we are talking in a power system, how the power is flowing from one direction to other direction, when the relative angle at one point is greater than the other, then power flow. So what happens is, by using appropriate control, the EMF induced at this point will be made at a larger angle than the grid. Okay, then only power can flow. That is the basics. So the disadvantage of this method is that power efficiency is low, as I told you earlier, because MPPT cannot be extracted. Then high power fluctuation will. So whatever, whenever your grid is having any kind of distortion, directly that will be reflecting to the machine. So that is also not good. So now coming to the variable speed wind energy conversion system, there we can see SCH, but you can see the configuration is different. So here you are connecting two back-to-back converters. So what happens is, if your machine is operating, so here definitely there will be a gearbox is there, because this is actually gearbox. So with the help of gearbox, what happens is when the machine is operating at a variable speed, whatever be the speed, according to the speed, the power will be extracted. But again, as we know, it will be limited to plus or minus 10% slip only. Okay, so it can be at any speed, so it doesn't matter. So whatever be the speed, according to that, it will be taking the power. Then with the help of DC link, it will be maintained constant at a constant DC link voltage. And from there, we are having a grid side converter. So grid side converter now will take care to make it as a fixed frequency, which is related with the grid. So definitely the converters which are connected to the grid will be, it must ensure the synchronization. Okay, otherwise everything will fail. So now coming to the variable speed wind energy conversion system. So one thing already we have seen, one is nothing but SEAG in this particular configuration, which is having a back-to-back configuration. But this is actually having a major disadvantage, because you see SEAG, when it is directly connected to the grid through this configuration, it is actually using two full converters. So basically this all generators are individual generators are generating power in the range of megawatt. So for handling that megawatt and thousands of amperes of currents, these converters, whatever you are using, should be a full converter, which means the cost is huge. So for extracting plus or minus 10% of power with this much converter is not a great idea. So there are actually disadvantages for this scheme. So then later PMSG and DFIG, these two, like what I can say, induction generators became popular. One is induction generator, and PMSG is actually a synchronous generator. They became popular. So here you can see the configuration of PMSG is exactly same as what we have seen CAG earlier. But the advantage of PMSG is we don't want to give any reactive power, because it has permanent magnet inside. They will be providing the sufficient reactive power needed for the machine. And now another one more thing is that here, but we know the flux which is produced or which is already there inside the PMSG is not having a very pure sinusoidal shape. It is having a trapezoidal shape. So what have to be done is, then the role of this converter is little huge, so that it has to make it first of all proper, to make it as a proper sinusoidal one, because then only you can integrate with the grid, because you cannot integrate like any power or any current you cannot pump to the grid with is not having a proper sinusoidal shape, which means if you are doing so, you are actually introducing a lot of harmonics into the grid. That is not at all allowed. So this configuration is actually good, but it is having a full rated converters are used there. And another one more thing is, PMS is having a drawback in such a way that inside the machine, when we are looking into, like inside the tower, there are having different other mechanisms which are actually used for tilting the complete drivetrain if it is going wrong in terms of some speed. Because for any wind generator to start, it has to, as I have shown you earlier in the wind power wind velocity characteristics. So generally the wind at 3 meter per second wind velocity, only most of the machines will start generation. Below that, it is not possible. And the rated wind velocity is mostly 9 to 12 meter per second. That is almost like at this point. And after that, no, it is not like it can generate at any wind velocity. So there is a limit. So generally that limit wind velocity is called as the cutout wind velocity. That will be ranging from 22 to 25 meter per second. Okay, in that range only it is possible. So what I mean to say here is, since all these possibilities are there, so sometimes there is a need, like I have to, when the wind velocity is increasing because of some natural phenomena or something or the other, I have to arrest the wind turbine at this particular point. So inside there are some mechanisms like yaw control and some other controller. So what happens is, lot of other motors are actually there in the tower. Okay, in the tower inside this. So which is used for turning the entire drivetrain in 360 degree. So what happens is the magnetic field of all these people will mutually interact each other, and after some years, approximately 25 to 30 years, this PMSG's magnetism will be slowly losing. So that is the main disadvantage of the PMSG based wind energy conversion systems. So now coming to the DFIG, you can see that compared to the other configurations what we have seen, we are not connecting back-to-back converters directly to the stator, whereas it is connected to the rotor side. So you can see the stator is directly connected to the grid, whereas the rotor is connected to the grid through two back-to-back converters. So advantage of this scheme is that you can even extract power from the rotor, and that can also be pumped to the grid, which means from the DFIG stator, power will be going to the grid. From the rotor also we can take power, and that can be given to the grid. So additionally, this can give some more power. So what happens is, DFIGs can generally operate at a slip of plus or minus 30%. Okay, so what happens is, if this is the case from the stator, if I am pumping a power of P from the rotor it can pump the additional power of 30%, because no, I think everybody will be remembering what we studied in the fundamentals of induction machine. So generally the power of the rotor is nothing but the slip times stator power. So if the stator power is PS, rotor is available with a power of slip time PS. So that is nothing but 30% of PS is available. So PS plus 30% of PS will actually pump to the grid. So actually DFIG is actually having a capability of generating 130% of the power, which is actually more than the rated capacity of the machine. That is possible. And here again, the full speed is not possible, because this can handle only up to plus or minus 30%, right? And here also we have gearboxes. But the major disadvantage of DFIG, since it is increasingly popular worldwide, the main focus of the today's discussion will be about DFIG. So let us see from this, what is a schematic? This is a schematic diagram for DFIG. As I told you earlier, the stator of the machine is directly connected to the grid, whereas the rotor of the machine is connected to the grid through back-to-back converters. So let us see what this back-to-back converter does. So first one is actually a rotor side converter. So we know that here, if you are seeing the difference between the configurations, here we are not using any capacitor bank, because inbuilt this person is having like magnetic flux production capability because of the magnets. But here we are not connecting any external capacitors, but all the machines, all the wind generators need reactive power support, then only it can generate. So what happens here is, here the rotor side converter, this particular converter with the help of the capacitor will be providing the sufficient reactive power requirement for the machine in this direction. Okay, that is possible. So that is the biggest advantage. We don't want to take anything from the grid. So as we all know that whenever we are connecting anything from the grid, the important thing to be noted is we have to always maintain the power factor of the grid. So we have to always maintain the power factor of the grid at unity. So which means like you should not consume any reactive power from the grid. So that is actually possible with the help of DFIG. So with the help of this rotor side converter with the capacitor bank, the sufficient reactive power required for the machine can be pumped directly from here. So no need to take anything from the grid. So another one more thing is, like with the help of these two converters, GSC and RSC, bidirectional power flow is possible, which means like by appropriately controlling these two converters, we can extract power from the rotor and that power can be pumped to the grid. So you can see that already this is flowing, and here this additionally can be made possible by doing so. And then we can see there is a grid side converter. So the basic role of the grid side converter is to maintain this DC link voltage constant, because whenever we are consuming something and when we are trying to inject reactive power here, there is a tendency like this may fall. So GSC will take care of that and it will make this constant. So again, another thing is, by chance, by when there is any grid distortion, if any some issues which are happening in the DFIG, sometimes it need additional reactive power, especially during unbalance and all. That time, with the help of DFIG, the needed reactive power can be pumped like this also. So again, no need to take from the grid. That possibility is also there. Solely we are telling unity power factor operation at grid terminals, and then also we will be maintaining the sinusoidal current in the grid. So even though we are telling a lot of things like this, the major disadvantage of DFIG is it is very sensitive to unbalance. So what happens is, let us assume like there is an unbalance of 10% in the grid. So if there is a very small unbalance also, huge unbalanced current will be flowing through the stator. So these currents actually is they will directly go to the machine. So what happens with the stator currents is, because of this, since the stator and rotor are magnetically coupled through the air gap, this huge stator current will have a major impact on the rotor. So what it will do is it will increase the rotor voltage like anything, and huge rotor currents will flow. So what happens now? Already these converters are capable of only handling 30%. It cannot handle this infinite current and infinite voltage. So what happened? Obviously, when large voltage and current is coming, taking the product of that, the overall power is high, which means this capacity of the converters is not enough to handle that, and immediately the rotor side converter obviously will burn. Okay, so in order to avoid that, generally in the industries, what they will do is, or in the real time, what they will do is, these three legs will be conducted through a converter through a resistance. Okay, so that is generally called as crowbar. So once something like that is happening, so these devices inside that, the power electronic switches will be activated based on the voltage and current. So they will be activated in such a way that immediately the DFIG will be connected through the rotor crowbar and will be grounded, so that the device can be protected. But once you are doing so, we know that once the stator is connected with something and internally or externally shorted, it will act like an SCIG, and immediately it will lose the control of this DFIG. And obviously, since the machine is facing unbalance, it cannot run further and it has to be forcefully shut down. So this is what is generally happening in the industry. So another one more issue is that slowly when this DFIG voltage and current is increasing, what happens is this capacitor is there. Na? So this voltage will show a tendency. It was already constant. It will show a tendency to increase like this. So that is also not good. So then this also will go further. It cannot pump the power. So it will lead to a complete damage of the machine. And if you are continuing like that for some time, it can create severe issues to the grid also. So if we can see that, what are the effects of voltage sag in DFIG? Basically, we know voltage sags, or whatever we are calling as unbalanced, they are symmetrical and unsymmetrical in nature. So let us see what happens with the symmetrical grids. So if it is symmetrical, so stator and rotor currents will increase. So why I am telling like this is, let us say I want to pump a power of 1 megawatt to the grid. So whatever you are pumping, the terminal voltage is nothing but the line voltage, that is nothing but 400 volts. So 1 megawatt divided by 400, it will have some current, right? So if you're having a symmetrical grid voltage, the meaning of symmetrical grid voltage is, earlier I was having 400 volt, and now my voltage, let us assume it is reduced to 390. So what happens? Power divided by this much reduced voltage, your current will be more. Nothing will happen. If all the, all the phases are having a balanced grid sag, nothing will happen. Only thing is like you will be able to pump the same power if you are within the rating of the machine with a higher current that you can see here. Only the current will increase. Nothing will happen. So it is still stable. Nothing will happen unless otherwise you are within the rated current capacity. But that will not be the scenario in the case of unsymmetrical sag. So you can observe here, during unsymmetrical sag, lot of disturbance will be there in the machine in the terms of oscillations of 100 hertz. I will explain to you in detail in the upcoming slides. So in addition, there will be harmonics in rotor current, and you can see that your stator currents are unbalanced with lot of issues. Whereas you can see here, this was very smooth, but here the scenario is different. So active and reactive power, electromagnetic torque oscillation, DC link voltage, so lot of issues will come. So because of this only, there are grid codes available for like according to the Electricity Act. So definitely we have to follow that, those who are connecting anything with the grid. It is not like that whatever you are generating, we can, just like that, we cannot pump to the grid. Okay, so if you are having any problem at the end of generation, or if you are having any problem at the grid side, like we have to still connect it to the grid, and that is what is called as low voltage right through. So it is the responsibility of the grid operator to continue pumping the power to the grid even though you are facing some issue with the grid. So before going to the major details, let us see these are the challenges involved in the power control of grid connected induction generators. First of all, synchronization is the important factor. So not only for induction generator, if it is solar or wind or whatever, if you're integrating with the grid, grid synchronization is very important. So without proper synchronization, you cannot pump anything to the grid. And another one more thing is your rotor speed. Because as I told you, when you are having unbalance, so once you are having some distortion with the grid, either it is unbalance or harmonics, that will be reflecting on your current. So if your current is not proper, torque is nothing but P by omega. So if your current is not proper, your power will not be proper. So power will have all the fluctuations. So if your torque is fluctuating, the meaning of that is your rotor will go back and forth. So your rotor speed is also pulsating. So simply with the normal algorithms, what people are telling directly, you cannot calculate the speed. So for this, especially for under unbalanced or distorted grid conditions, special measures have to be taken care. And we have to ensure that the power control is possible even with low voltage right through. So these are the important things we have to take care. So now let us see, this is the basic space vector diagram of a induction generator control. So I don't want to say so much to make you confused, only few points I have to add here. Actually, there are two types of control. One is stator flux oriented control. Okay, one is stator flux oriented control and another one is the stator voltage oriented control. So the meaning of the voltage, or first let us talk about this. So when you're talking about the stator flux oriented control, the meaning is that the entire flux inside the machine, okay, let it be phi-s, that will be aligned to the d-axis, and the total voltage will be aligned to the q-axis, because we know that voltage and flux are like apart from each other by 90 degree. So your flux will be completely aligned to the d-axis and voltage will be completely aligned to the two-axis. Like that only we will do the control. So what happens if your flux is completely aligned to the d-axis? I will have only the component of flux as phi sd, right? Because my total flux is here. My phi sq component will be obviously 0. Similarly, when I am fixing the flux here, obviously my voltage will be here. So my total voltage will be available at VSQ. I will not have any component in VSD. Am I right? So I'll not have any component VSD. My VSD will be obviously 0. So total flux will be phi SD. So there will not be any phi SQ, that will be equal to 0. Similarly, this is the case. So actually, this is a fundamental information. Why I told this is the fundamental information needed for PLL operation also. Okay. So now, what is the significance of synchronization technique in power control? So whatever, I am again repeating, whatever be your renewable power or whatever be the generation, synchronization is important. So basically by synchronization or by doing so, in the power control, what is the role of synchronization is, it is basically for generating reference currents or voltages for power control, okay? So basically by synchronization, we'll be getting the accurate phase, frequency and amplitude of the fundamental component of grid voltage. So I think everybody may be familiar with this. This is generally used for the vector control. So what I want to say here is, when we are going for power control, especially in vector control mode, what the meaning of vector control or why the need of vector control is, let us say I am in ABC frame. So this is ABC. You can see A, B, and C. So this is my three-phase voltages. So controlling the three-phase voltages is not so easy, because when you are talking about the stator, okay, let us assume that I am talking about the machine which is having stator. Stator is again three-phase with R and L. Similarly, you will have rotor also here, a star connected rotor also is here. Let us assume that. So if I am writing the equation of voltage for one phase, I will write VA equal to RA IA plus LA DI by dt plus mutual inductance. So how many mutual inductance will come? 1, 2, 3 will come. So since with a small air gap, you are having another one more rotor here. So the effect of rotor also will come here, which means in one equation, you will have 6 mutual inductances. So controlling those kind of complex equations are not possible. So because of that only, people are moving to the vector control. So what happens from this three-phase frame, you will be moving to a stationary alpha beta frame, and from there you will be moving to a synchronously rotating frame. So in synchronously rotating DQ frame, the equations of power are like this, okay? So I'll give you some references of our own papers, like those who are interested to see in detail, because here I cannot tell so much mathematics. So you can go through that. So control of real and reactive power. So P, we can see that the active power P generally will be represented as 3 by 2 into VD IGD plus VQ IQ. So what is this VD? VD is nothing but the grid voltage converted to vector by converting to the synchronous reference frame. Similarly, IGD and IGQ are the grid currents. Similarly, Q can be represented like this. So the main discussion here is not that. So I said, if you are going for a stator flux oriented control, I will not have any voltage in VD. Yes or no? So if that is the case, this equation, first equation will be reduced to this, right? So I can write as P equal to 3 by 2 into VQ IGD, because this term will be going to 0. Similarly, the second term here, this term will go to 0. Correct? Only this will remain. So what I mean to say is, this is a fundamental thing what we are using to fix the reference current. So earlier we said, I want to pump 1 megawatt. So for 1 megawatt, this P reference will be 1 megawatt. Okay. And VQ we can easily find out from the stator voltage. So P divided by 3 by 2 into VQ, that will be the reference current what you are setting for the converter to pump this much power. Is it clear? So similarly, if I don't want to pump reactive power Q, then I will put Q as 0. Obviously, my IGD reference will be 0. Whereas if I want to pump reactive power Q of 100 var, then 100 will come here, 100 divided by minus 3 by 2 VQ. That will be your current for pumping that much reactive power to the machine. So you can see here, when we are moving from alpha to DQ, they are involved a person omega t. So this omega t is nothing but theta. This is information obviously we have to get from PLL. So this is the importance of PLL for power control. I think it is clear. So DQ components, whatever you are talking about here, in terms of voltage and current, all these people or all the persons who are involved, we will be getting from the vector control. So I would like to quickly take you through the vector control, not in detail, very quickly. So we know like there are 3 frames of reference. First is ABC frame. Okay. So from ABC frame to alpha beta frame, whatever you are doing is known as a Clark's transformation. So in the Clark's transformation, basically the meaning of transformation is whatever vectors you are having, that vector is the resolved component of the vectors in the other frame. So for example, if I want to write what is V alpha, I have to say what is the resolved component of A on alpha, what is the resolved component of B on alpha, and C on alpha. So what is V alpha? V alpha is, so now you ignore about this 2 by 3. I'll tell you why it is coming. Now remaining you see, I can say that my A and alpha are completely aligned. So what is my component of A on alpha? It is nothing but VA only. Whereas if I want to align my B with alpha, so what is the angular difference between them? B can be aligned to alpha if I am moving B in this direction by 120 degree, correct? So that is nothing but VB cos 120. So cos 120 is minus 1 by 2. So from this only VA minus 1 by 2 VB is coming. Similarly, if I want to find out the resolved component of C on alpha, I have to rotate C 240 degrees, right? So that is nothing but VC cos 240. That is nothing but minus 1 by 2 VC. Okay. Now you will be wondering like from where this 2 by 3 came. So we know that for a balanced three-phase system, generally we will write VA plus VB plus VC equal to 0, right? Generally we will write. So the basic fundamental behind the transformation is whenever you are moving from one frame to another, there should not be any power invariance, because by transforming your power will not increase. It should be the same. So here if VA plus VB plus VC equal to 0, this part I can rewrite. I can write this as VA minus 1 by 2 of VB plus VC. Am I right? Taking this 1 by 2 minus 1 by 2 common. So if I'm taking from here VB plus VC, what is my VB plus VC? Because the other side is 0, it is nothing but minus VA. So what will come? 1 by 2 minus 1 by 2 into minus VA. So that is nothing but VA plus 3 plus 1 by 2 VA. That is totally you will get as 3 by 2 VA. I think it is clear. Are you getting confused? So VA plus VB plus VC is 0. So from this, what I did, I have taken minus 1 by 2 common and remaining inside is VB plus VC. So by taking that minus 1 by 2, VB plus VC I have substituted from here as minus VA. So obviously it is VA plus VA by 2, that is 3 by 2 VA. So what happened by using the transformation is you have multiplied almost your V by 2, 3 by 2 VA with V alpha. So that is not at all allowed. Na? So if by doing the transformation, the power is increasing, for increasing the power from 10 watt to 300 watt, we can do 3-time transformation, but that is not possible. That is not correct. So to compensate this only, this 2 by 3 is multiplied. I think it is clear now. So now coming to V beta, when you are talking about V beta, same way. How are you resolving the components to this? So already A is here and beta is in 90 degree. Obviously, there will not be any component of A on beta. So only that is not here. Whereas the component of B on beta is nothing but, so we know A and B are at an angle of 120 degree. This is at an angle of 90 degree. So obviously this angle is 30 degree, right? So you can transform B to beta with an angle of 30 degree. Similarly, from C to beta again will be with 30 degree. Okay, how this 30 degree is coming is, this is beta, so the component of B on this side. Okay, so this angle is actually 30 degree, na? So this angle is 30 degree. So if I want to transform to B, so only this negative is coming, because actual my beta is in this direction. When I am transforming to get to beta, it is actually minus VB. So minus VB cos 30. Similar, this is plus VC cos 30, you will get the transformation. Okay. So finally, when I am going to this alpha beta to DQ conversion, the same thing. So we have already alpha beta frame, and then when we are going to the DQ frame, you can see it later slowly, use the same transformation. So how it is coming, I can tell you quickly. So this is my alpha. So when I am finding out the components of, because already we have got alpha beta. So when you are moving from alpha beta to DQ, so it is nothing but V alpha into cos omega t and V beta. So from beta, if I want to come to D, so I have to move 90 degree plus omega t. So that is 90 plus omega. So similar way, you can find out the transformation. So in a similar way, we will be generally finding out sine omega t, because here you know what is alpha and beta, but we don't know what is sine omega t and cos omega t, right? If you know these two, then only you can go for the transformation. So what is this sine omega t and cos omega t? So if this is omega t, this is also omega t, right? So if I want to complete this as a parallelogram, how can I write sine omega t? Sine omega t is nothing but my opposite side by hypotenuse. What is my opposite side? Opposite side is belonging to alpha. That is nothing but Vs alpha. So V alpha divided by hypotenuse generally will be, if this is V alpha and if this is V beta, my hypotenuse will be under root of V alpha square plus V beta square, right? So that is how we will find out sine omega t. So what is cos omega t? Cos omega t is adjacent side by hypotenuse. Adjacent side is V beta divided by this. So why I stress this is, this way of finding out sine omega t and cos omega t is known as open loop PLL. Okay. So this is open loop PLL. So Synchronization techniques you can understand by this. Synchronization techniques are of two types. One is open loop method and other is closed loop method. But this open loop method is not effective. So those who are working in this area, please remember open loop method is not effective for any grid integration because your grid voltage is not always balanced. It is having lot of issues. So then we have to move for the closed loop method. So closed loop method, we will see what is the closed loop method. So PLL is widely used. So this is open loop PLL. So actually closed loop PLLs are widely used for this purpose. Okay, so let us see, this is a basic structure of a closed loop PLL. In the case of closed loop PLL, you can see that there is a phase detector, there is a loop filter, and there is a VCO. Okay, so the basic role of the phase, you can see that. So first, whatever you are sensing as ABC voltages, it has to be converted to alpha beta, and then you have to find out DQ. So we already seen that my VD will be 0. Okay, so my VD will be 0 when we are going for a stator flux oriented frame. So that VD is actually set as reference here. So my reference will be equal to 0. Okay, and then there is a phase detector. So the role of the phase detector is to compare this reference and this one and to give the error signal here. So what loop filter will do is loop filter will minimize the frequency error of the loop. And you can see that an additional component is getting added here. That is nothing but the feed forward omega. So this generally will be corresponding to the 50 Hertz frequency of the grid. So we know that the supply frequency of the grid is nothing but 50 Hertz. Even though it is not constant always, it is 50 Hertz. So generally what omega f of people will give is, omega is in radians per second. So they will be giving us 2 pi into f. So 2 pi into f is nothing but 2 pi into 50. So this will be generally inserted as a constant of 314.16. Okay, that much radians. So what we'll do is by adding this error omega with the actual omega, this integrator will be integrating that, and obviously we will give theta, because as we all know that omega is nothing but d theta by dt. So if I want to find out theta, obviously I have to integrate omega. So this is actually the role of a VCO. So VCO will take care of the conversion of your omega to theta. But even this, here you see one important problem is there is, like we know always your grid frequency is not constant, but we have inserted a constant frequency. And another one more thing is, when the grid is having some problem, when the grid is having some kind of distortion, your VD will not be constant. It will not be 0. It will have some other value. So even this PLL will give poor performance under unbalanced grid voltages and harmonics. Okay, so I'll just quickly tell you what is the effect of unbalance. So what happens during unbalance is, during unbalance, you will be having an additional component of 100 Hertz signal. So at this point, if unbalance is present in the signal, from this point onwards, if you are having unbalance in the grid, you can see some 100 Hertz oscillations are coming. Basically, it is because of inside the machine, we all studied like for an induction motor operation, flux will be there, it will be rotating in the clockwise direction, correct? So what happens during the unbalance is, so that is this flux. So in the unbalance, what happens, an additional flux will start revolving opposite to that. So these two will interact each other. And if you are seeing that, we can see two frames here. Q plus is the positive frame and Q minus is another one more frame you can see. So if you are seeing them, or the angular distance between them, you can see they are apart at an angular displacement of 2 theta. So this 2 theta is the person leading to all kind of oscillations that will produce oscillations in the voltage, oscillations in the power, torque, speed, etc. So what happens, whatever we have assumed sometime before for PLL is VD is 0, but your VD is not 0 under unbalance. Similarly, you can see under harmonics in grid voltage, you are having harmonic frequency related to what is the frequency of the harmonics. Let us say if I am having fifth harmonic content, accordingly, you will be having frequency component inside. Then also your VD is not 0. Similarly, another issues like when there is phase jump or DC offset, then also your VD is 0. So this is the effect. So what happens when there is unbalance, harmonics, DC offset or phase jump, you will be having additional frequency terms inside. So as I told you, unbalance will produce 2 omega term, phase jump will produce 2 omega term, whereas you can see DC offset is producing omega term and harmonics is producing 6 omega term. Okay, why harmonics is producing 6 omega term? It is nothing but the relative frequency, because 5 omega is in this direction and omega is in this direction. So the relative frequency of them is omega s minus of 5 omega s. Ultimately, it will become 6 omega. So these things we have to take care. So what happens is, so basically whatever you are telling, those kind of fundamental PLL will not help in the case of grid synchronization. So if you are going for a balanced system, what we are assuming is my VD will be constant and I will be getting a proper PLL output. Whereas if my grid is unbalanced, my PLL output also will be distorted. So basically, this kind of scheme can give fast transient response under balanced grid voltages, but under distorted grid condition, they will not get proper output. Moreover, your steady state frequency error will come because we have assumed frequency as constant, but that is not the real scenario. So this is the thing. Whenever you are going for a proper PLL, which is integrated with the grid, you have to go with a filter inside. Okay, so what filter will do is, if you are keeping a low pass filter, whatever disturbances are coming here, actually this is VD. Okay, this is VD and this is VD. This is VQ. So whatever disturbances are coming in the VD, when it is passing through the filter, you will be getting a proper constant signal inside as delta omega, because your filter will bypass all these harmonics. So then you will be getting a proper response. Okay, then again one more point has to be taken care is this omega ff. So I am going to the next part. So what you do is, instead of giving it as a simple constant, we have to calculate what is the actual omega, and that has to be inserted inside. So for that, references like a few of my own publications are added here in this. You can see later in detail to see that. So main advice for the people who are working with grid integration is, don't assume anything as constant, because your voltage or frequency, nothing is constant. You have to find out the real-time values of that, and then only you have to integrate, then only your proper grid synchronization is possible. So this you can see from the results, like whatever be the harmonics or whatever be the unbalance or offset, we are able to exactly find out the proper theta under all the situations. Okay, so this we have to definitely take care. So now when coming to the rotor speed, that is another important problem. So rotor speed, as when you are those who are working with the, because both the whatever be the sources, no, who are working with the sources which are going to be integrated with grid, PLL is an important thing to be considered. But whereas when we are talking about the rotor speed, this is only for people who are working with the wind. So what happens is, there are different methods available to find out rotor speed. So what people used to do is, anybody is asking for time? No problem. So when we are talking about the rotor speed and position, what happens, you can see here people are measuring the stator voltage, they are measuring the rotor current, they are measuring the stator current. So many parameters are coming, and this is a complex mathematical thing which is involved. So it is not advisable to use so many sensors, because every sensor is having some sensitivity. If you are conducting information, some 10 sensors, and again you are multiplying, dividing, and so many things, it may lead to delay in computation. It may lead to inaccuracy. So all these issues will come. So it is not advisable again to go with a lot of sensors and transforming from one frame to another frame multiple times. So you can see most of the methods. So this is one method. What they are doing here is, they are actually finding out the current. Okay, they are transforming to different frames and finding out. So when doing so, what happens is, again, as I said, saturation problems, inaccuracy problem, lot of issues will come. So this is actually an open loop method. Okay. So similarly, there are closed loop methods. You would have heard about MRAS method, model reference adaptive system. So in that method also, what they are doing is, in reference, two models will be there. One reference model, another one is an adaptive model. So reference model generally will be taking care of, or it will be based on the equations which are independent of speed, whereas adaptive model will be based on the equations which are dependent on speed. So they will be trying to compare both of them, and when it is coming equal, they are saying, okay, this is happening because of whatever is a parameter inside, that is nothing but the speed. But this is again an indirect method. So no need to go for this much complexities. Easily we can find out with only the stator voltages and currents. That method is generally called as a rotor position phase lock loop, which is nothing but RPLL, similar to the grid side PLL. So what we are doing is, using the normal grid side PLL, we can find out sin mu and cos mu. And another thing is, like, no need to actually use the rotor sensors. We can actually measure. Instead of measuring, we can actually compute the rotor currents. Okay, with the computed rotor currents, you can find out the actual speed, and this speed, with the help of, as I told you earlier, for a normal PLL, with the help of low pass filter, you can be given to a rotor phase lock loop, so that it will lock properly and will give you proper results. So here also, so remember, those who are working with any type of PLL, definitely a filter is an important part needed before feeding any signal inside in the form of feed forward. Okay, so that is an important thing to be noted. So this also in detail you can see from this publication. So here the basic thing what we did is, like, we didn't go with any rotor measurement. We have done only with the computation of the rotor current. So here also you can see everywhere, whatever be the rotor speed, we are able to exactly do that. So when you are going for grid integration of machine with the rotor, so definitely those who are working with the wind, they have to find out the speed computation in such a way that it will be able to give proper results under any distorted grid conditions. Okay. So few experimental result samples also are shown here. Also everywhere you can see they are properly tracking. Yeah. So actually, since it's a 2 session, already I have taken 15 minutes extra. So can I take another 5 minutes? What are the comments?
Yes, ma'am. Yes, sure, ma'am.
Yeah. So basically, one thing I have to tell you, generally, you have seen how is a kind of power control I told you earlier. So what we can see here in the case of power control is we will be generating reference currents like this from P and Q by dividing with the voltage, right? So basically, these currents generally will be fed to the control loop in such a way that it will be, because if you are setting, I want to pump 1 megawatt power, and I don't want any reactive power to be taken from the grid. So I'll put this as 0 var. And if I want to put pump 1 megawatt from the machine, I will definitely put this PS as 1 megawatt. So by using this, I can find out what are the stator currents ISD and ISQ, right? So after finding that, there are fundamental machine model equations for rotor. So using that, by giving these two currents, whatever we just now found out, we can fix what are the reference rotor currents. So by fixing the reference rotor currents, if you are giving this information to the control loop, so control loop will be having IGBT and all other controllers what you have seen earlier in the picture. Obviously, what it will do is it will pump this much power without taking anything from the grid. Similarly, in the grid side also, similar procedure is there. You will be finding out how much is the power I can pump from the grid, or do you want any reactive power from the grid, or you want to pump anything from the grid. Based on all these things, we will be fixing the loop. Here, one important thing to be noted is GSE main role is to control the DC link voltage. So if your DC link is actually 400 volt, so you will be giving this 400 volt as reference, you will be comparing the actual and this loop will run. Okay. So this is a fundamental thing. But actually the main concern is not about the normal operation, because none of the time your grid voltage is balanced. If you are seeing the grid codes or any other electricity act related to codes, you can understand that always the grid voltage is unbalanced, which is ranging from -3% to +10%. So these will be the effect under the machine. So machine will be undergoing lot of negative flux. This is what I said. When the actual flux is in this direction, your negative sequence flux in this direction, which will be trapezoid in nature, and it will be disturbing the machine like anything. So in terms of rotor flux, in terms of current, and a lot of issues will come. So what I have to say here is, those who are doing for power control, your main concern is, instead of pumping the reactive power and active power, what we fixed early, P and Q we set now, instead of that, we have to minimize these oscillations also. So we have to take measures to minimize those oscillations. So then what we have to do is, normal power equation, generally this is what we have seen earlier. Now what we can see is, additionally this VQ will be having negative sequence voltage and negative sequence current. So what happens is, this VSQ will have VSQ plus as well as VSQ minus. Similarly, your current also will have plus and minus. They will mutually multiply each other and it will give to 8 components. So these mutual components, which are product of plus and minus terms, are the reason for oscillation. So obviously we have to, or definitely we have to eliminate those elements. Otherwise it will be disturbing the machine. Your machine winding will go. And when you are continuously running that, this will inject harmonics to the grid. That is also not allowed. So we have to take measures. So one method what we did is, we are calculating new set of reference currents for forcefully making these elements to 0. So you can see that details later from the references what is given below. So by taking new set of references, what happens is that references will be added with the control loop, and for both grid side and rotor side converter. And by doing that, you can see this is the effect. Under balanced grid condition, my QS was 0 and I was able to pump the power whatever I set as limit. This is actually in per unit, and this is tested for a 250 kilowatt DFIG. So what happens after some time when I am introducing unbalance, you can see lot of pulsations are coming everywhere. Then by activating the controller, it is getting suppressed. Okay, and you can see that after activating the controller, the currents are actually balanced, and whatever all the disturbances coming, that is taken by the grid side converter. So we were able to minimize oscillation to 70 to 80% with this method. So this was the experimental setup what we developed for that. And here also from the hardware results also you can see the similar performance from the methodology. Further, this is another one more method. Concept is the same, but actually we know the main cause of the problem is natural flux. So we try to directly minimize the natural flux, and by that also we got similar results. So that can be seen here with this one. So this is one interesting thing what you can see here. Here you can see this is actually the flux which is rotating inside the machine. So we can see that the flux is taking a what is that circular path which is rotating at a constant thing. So always it will be like that. So once unbalanced that you can see it will start rotating like this in a mismatch fashion. So that is what you can see in this much time. So you can see clearly from the time 8 seconds when we are turning on our controller. So here we are turning on the, after that again it is becoming balanced. So how it is becoming balanced is by doing this methodology, we are injecting actually currents in such a way that it will produce a negative sequence flux which will be damping the additional flux which is rotating inside the machine. So only the flux is actually coming back to 0. Okay, so these are some case studies what we have done. Here also the similar results we obtained. So that is all about the thing. So ultimately what I have to say is those who are working with the renewable energy integration with the grid, you have to take care of two things. Most importantly, one is PLL and other one is RPLL. So PLL should give proper synchronization results under any distorted grid conditions. Whereas if it is induction generator or PMSG, your RPLL should give perfect synchronization input for the rotor. And in addition, those who are connecting or going to do power control, you should definitely consider this low voltage right through problem, because whatever be the problem which is encountering the grid, whenever problem is there also, you are not just like that, you are not allowed to pump the power. So you have to take appropriate measures to take pump power to the grid when there is having any grid distortion. So your control should be having that additional capability also to take care of the distortions. Okay, thank you. So if anybody is having any queries, then we can address.
Thank you, ma'am. Thank you for the wonderful session. So all the questions are in the chat box. Firstly, I would like to invite Professor NVD Chaudhary to clear the doubts. Yes, sir.
Yeah. The one question was from Pradyumna Prasad. Approximately when will Indian grid become fully smart? We are expecting next 10 to 12 years to make our total Indian grid fully smart, because for a smart grid, we need lots of sensors and communication channels in between that it will take some time to install. Therefore, then our target is 2030 to get the Indian grid to be smart. Another question I find from Dinesh. Power generation by consumer can be consumed by another consumer. Can it be feedback to substation? Oh, yes. Yes. A power generated by the rooftop solar can be used by the house itself, or this rooftop solar can be fed directly to the grid. Yes, possible. Another question from Sandeep Chaudhary is, what factors are considered in smart grid for reactive power management? In smart grid, the reactive power management in general from point to point in transmission, distribution, and generation, mostly from the distribution and the consumer point, this reactive power is measured in terms of Q, and that can be in normal smart grid, in normal grid, that can be managed very quickly by using all those devices used for controlling the reactive power. Similarly, in the smart grid also, all these devices will act automatically after getting the signals from each and every point. Yes, it is possible. Now over to Madam.
Yeah, actually, the question to me is, can we build rooftop wind generation system? Yes, obviously it is possible, but how you are seeing normally in the normal big generators with towers which are connected to the ground, that is not possible, because the important thing is that, like, how much weight you are giving above, proportionally more than that will be there under the ground. So then only it will support. So like, it is possible, but lower capacity only is possible. 5 kilowatt, 10 kilowatt, like that only is possible with rooftop. Second question is stator flux or stator voltage. How both generated in stator? No, actually it is up to us. How are we taking the frame of reference? As I told you, I can take in such a way that I am going to align my total flux in the d-axis. Then it is called as stator flux oriented frame. Whereas if you are taking it the other way, it is called as stator voltage oriented frame. So based on that, whatever is the frame of reference you are taking, if I am taking the flux as the reference in d-axis, my VD will be maximum, and my my VQ will be maximum and my VD will be 0. Whereas if I am taking the other way, obviously my VQ will be 0 and other will be there. So accordingly, you will be getting, or you have to modify the control equation. That's all, nothing else. Can PMSG be connected with back? Yes, obviously PMSG be connected in back-to-back. No, actually it is not possible. It is not possible. Why? Because if you are connecting with PMSG directly to the grid, because already the flux inside the PMSG is not purely sinusoidal. So what happens, like, directly or indirectly or unknowingly, you will be injecting lot of harmonics to the grid if you are connecting PMSG stator directly to the grid. So mandatorily it needs a back-to-back converter there. Why we have to first transform to stationary frame, and then both stator and rotor are transformed to synchronous frame. So it is like, if you are transforming from one frame to another, generally why we are doing is, your first ABC frame is rotating at 120 degree, because all are mutually 120 degree apart from each other. So if you are directly moving from one frame to other frame, it can be done. It is not like it is not possible. Actually, this in between one frame is there, what is called as a stationary reference frame. Basically, it is stationary, it is not moving. So the possibility or the advantage of doing that is, you can move easily from the 3-phase quantities to 2-phase. There you will be getting only alpha and beta. From alpha beta directly you can move to DQ. Correct. So the relation between, or the angle between alpha beta and DQ is actually the information of PLL. So those are working with PLL, or if you want to make a PLL, definitely we need alpha beta in between. So the angular difference between alpha beta and DQ is only the PLL information theta. So definitely that is needed. I think I was able to. Yeah.
Thank you, sir and ma'am, for such an excellent and informative session. And once again, we express our gratitude for accepting our request to be an expert in this short-term training program. Thank you so much, sir and ma'am.
Thank you very much. Thank you very much for inviting us to such a August gathering.